1 5 8 8 3 3 3 3 3 plus 4 is 2 fifth 1 5 3 1 5 1 5 8 3 5 1 3 1 3 5 1 3 5 1 3 5 8 8 5 hold on 5 3 tonic tonic fifth tonic 1 5 8 3 tonic tonic 1 5 8 1 5 8 8 3 3 3 3 5 8 1
Io sono di Roma.
Io sono di Roma, piacere. Roma, piacere.
Ciao, Matteo.
Ciao Matteo.
Salve, io sono Matteo.
Io sono di Milano. Piacere.
Io sono con Luca.
Dammi blu.
Io sono di Roma.
Salve, io sono di Roma.
Io sono di Milano. Piacere.
Ciao, io sono Anna.
Salve. Io sono di Milano.
Ciao, Luca, piacere, io sono Matteo.
Evaluated limits. I need you to know that evaluated limits is exactly the same here as it is for Calc 1, and I'm going to cheat. I told you I'm going to use some circular reasoning. What I'm going to do is show you how to evaluate based on the fact that we have continuity. Then I'm going to talk about continuity and use that to kind of fill in the fact that we're able to do this. Okay, so here's the how. I'll talk about the why in just in a little while. So the how. Whenever we're evaluating limits, I don't care what class you're in up through calculus. The first thing I want you to do is plug the numbers in. Just plug them in. If you don't get 0 over 0 or a 0 on a denominator, you're done. Plug them in. And we're using the fact that if you plug in a value and you get a number, a limit, then that function exists at that point. And in a neighborhood around it, you can find continuity. And in a neighborhood around it, I mean all the paths lead to that same value. That's what we're using here. We'll talk about if we have a domain that's defined, we're continuous on that domain. We'll talk about that in a minute, but that's basically what we're using. We're saying if this function exists, if it's defined at that point, you're going to be continuous at that point, which means that the limit has to exist, because if we're defined, the limit exists. If we're defining continuous, the limit has to exist. Therefore, plug in a number, the limit has to equal the value of the function. We're kind of cheating here. The idea from Calc 1 would be if the point exists and the limit exists, and limit equals the point, you have continuity. If you have this, the limit exists, the point exists, and the point's in that little spot, that creates continuity. So if we have continuity, i.e. it's defined, if it's defined with continuity, if we have that, then we can go backwards and say, if we have continuity, then the limit exists. And that's what I meant about we're going backwards here. So let's try it. Can you plug in your x and your y value? What is your x value? What's your y value? Have you already plugged this in? How much do you get? 3? Okay. 3. Y, well, 1, negative 2, okay, perfect. 1, negative 2, plug in, you get 3. Simplify, you get 3. You guys okay with that one? Right. Where's the weird one? We also learned this from Calc 1. Right side and left side are super fine as long as you have continuous functions. So honestly, plug the numbers in and see if they work. So just plug in 0 and 0. Let's see if we can do that. Can you plug in 0 and 0? What do you get? Come back here, folks. Just this part, just that. What do you get here? So something close to 0 from the right, positive. Something close to 0 from the right, also positive. You're going to get something close to 0 from the right, 0. So you're going to get 0, close to 0, but positive. Reason why it has to be right-sided because you have it under a square root. You can't get it from the other side. Okay, so you can't add it. That's the only reason why it's there. So this is e to the 0 over negative 1. How much do we get for that? That's it. That's it. That's evaluating limits. And now if you're okay with that one. We can make it nastier, but the idea is the same. So let's try, I'm going to give you one that's kind of nasty, and then I'll give you another one I want you to think about. So give it a try. Here's x, y, z. I want the limit of the following function as we approach the point 031, and the function is oh, don't worry. Worry. Yeah, that's what I'm talking about. Woo! What's the first thing you do with any limit, like ever? You just do that. Just plug it in. Just plug it in and see what happens. Hopefully I wrote it down right. I'm sorry. After you do that one, I want you thinking about the next example, please. What's the x value? Y value? Z value? 1. Instead of trying to do all of this math in your head, probably not a good idea. At least write out some piece of it. All right. So for here, I'm writing out e to the sine of. I do know that's 0, so I'm going to put a 0. E to the sine of 0 plus ln. That's got to be there. Cosine. That's got to be there. Pi. That's got to be there. But I would do things like this. 3 minus 1 is 2. So this is times 2, or you can put 2 pi. Does that make sense to you? I do just little stuff, not a whole bunch. It's crazy too hard to do that. How much is sine of 0? 0. How much is cosine of 2 pi?
1.
How much is that?
1.
Plus 0.
1.
Equals
0.
And then it's 1. Okay, yes, no. Easy, medium, hard. Plugging stuff in pretty easy as long as you know to do that. Now, did you think about that one as we were doing the problem? Did you think about that one? What's the first thing you always do with limits? Plug it in. What's it give you? Crap. Every other time we try to prove this doesn't exist. Now we're going to try to prove it does exist. There's a few ways that we can go about thinking about this. One of the squeeze theorem, which we're not going to do right now. We'll do it a little bit later. One squeeze theorem. Another one is, well, you can do some algebraic manipulation, or you can do a really cool trick sometimes that helps a lot. If it's not working for you, and you're like, dang, I don't even know, but you see a lot of x squared plus y squareds floating around. You see a lot of that. You see what I'm talking about? Number one thing, goodness, don't make me drink at night. Please don't start canceling this stuff out. I like crossing stuff out. I cross it out. Please don't do that. I swear, please. I'm baking. Please don't do that. Okay. Also, I don't want you to start factoring. You can't factor this. It's impossible. You can factor that, but it's not going to help you. You get your x plus y times this quadratic that's not factorable. So you go, what else to do with that? That's not going to help. What I do see is that, goodness, I know that this is true. As long as I let, right? This and that also be true. Sometimes we can trick our problem into thinking that it's polar. Make it polar. If you get 0 over 0, you see a lot of x squared plus y squared, 0 over 0, and you go, well, let's try to make this thing happen. If we do, we can let this go to r, well, x would be r cosine theta, so r cubed cosine cubed theta plus r cubed sine cubed theta. And now if you're okay with that one, for real. Yes, no, yeah? Do you see where this came from? If x is r cosine theta, then x cubed is r cosine theta cubed, r cubed cosine theta cubed. Same thing for the y. What's the denominator? What's that going to be? My next question, this is a really kind of interesting question. What's my independent variable? What's it going? What's x and y relate to up here? So what? X and y are only tied. Well, they're tied to theta, but they're also tied to r. Well, let's see what happens. If x and y go to 0, 0, what's x squared plus y squared going to? Then r would also go to 0. But look, it can't be negative, right? This is going to give us something that's positive, so plus, right-hand side. So if we're going to use that, then our R is a thing that's going to 0, but it's right side. Now, can you see something nice to do? Come on, quickly. See something nice to do. What are you going to do? Not yet. What are you going to do? You're going to simplify. How? It's the F word. Come on, what are you going to do? So if we factor, and we simplify, let's think about it. I don't care what this is. Tell me why I don't even care about what that is. What's the R doing?
0.
What's 0 times pretty much anything?
0.
And even if it's 0, I don't really care. So 0 times anything is how much? 0. Does that prove the limit exists? Yes. Yes, it does. We plug in the number, we actually got a number out. That proves the limit exists. And now if you're okay with that one. Question?
Why does the R have to go or 0 from the right again? What is that?
Well, a couple reasons. When we're, man, you could go absolute value. You could go absolute value, but you're never going to get a negative out of that. The absolute value R, if you take the square root of both sides, you get the absolute value of that R. We just go 0 plus and not have to do with a negative, honestly. So that's why. Not a very big thing. Just make sure you go 0. Can you do it for the next one? Can you see the substitution for the next problem? Because right now, if you plug this in, do you know what you get if you plug that in? Plug in 0, 0. What do you get? Come on, folks. How much is this? Times how much is this?
0.
This is 0. ln of 0 is negative infinity. ln, as you approach 0, it's doing this. That's what's happening. ln of 0, negative infinity. This is an indeterminate form. If only. Indeterminate form. So that is. Well, if we start doing stuff like, all right, let's let x squared plus y squared equal r squared, then we can change our limit to r ln r squared. Quick hit now if you're okay with the substitution. Please don't let your r squareds change to r's magically. Don't do that. X squared plus y squared is r squared. Are you following the math on this? Do you see why our r is going to go to 0? Now, that doesn't help you with the indeterminate form, but if you ever did limits of indeterminate forms from section 6.7 from Calculus 2, then you know that at this point, if you have 0 times some type of infinity, and you create this complex fraction, you change the 0 into a different, you change it into a different thing, change it into infinity. Now you have infinity. Notice this. What's 1 over 0? Oh, it's infinity. What do you do anytime you see infinity over infinity? Come on, L'Hopital's. Say what? L'Hopital's. So here, even if you move this down, L'Hopital's, how are you going to do it? Because you got 2 variables, 2 independent variables. How are you going to do that? But if you change it to 1 independent variable and we manipulate it, now you've got L'Hopital's. I'm not going to finish it. I want you to finish it. Try L'Hopital's here. So kind of a cool idea. I hope you like this idea. I liked it the first time I saw it. That's pretty neat. You go, what am I supposed to do with this? I don't know. Give up? No. Let's try to change it to polar. Let's make x squared plus y squared equal r squared. We got some substitution for x and y. Same thing here. As soon as we do that, even if we have indeterminate forms, you know what to do with one variable. You can start creating from 0 times infinity, infinity over, change it, make a fraction, over infinity, and then L'Hopital's. Head on if you're okay with that one for real. Comments, questions, anything? I can't help you if you don't ask. Yeah. Okay. Anybody else? Yeah.
How do you get 1 over r squared?
You force this thing down to a denominator. You force it. So you go, well, where do I want that? I want to create this.
So forcing it to get the different forms.
It's already an indeterminate form. What you're forcing it to be is a form that allows L'Hopital's. So how do I move this to a denominator? Well, you could do r to the negative 2. That forces it, right? Yep. You guys know what negative exponents? Okay. Well, what is r to the negative 2? Well, it's actually a complex fraction. There you go. Now it's infinity over infinity. You can't do anything with this. Please, I'm begging you. Don't go 0 times infinity. 0. Sometimes. That's D for done right there, though. You've heard that. Okay. Sometimes not. You gotta work with it. So you create this and you go, hey, let's make it 0 times infinity? No. Let's make it infinity over 1 times 0. That's infinity. Infinity over infinity, and then L'Hopital's. Okay, we gotta get on with this stuff. We're gonna talk about continuity right now. Listen, here's the rundown on continuity. A function is continuous on a region. If at each point in the region, we can find this little neighborhood around it, where we don't have any gaps, jumps, or boundaries. So basically, we say, if we have this point on the interior of a region, you don't have to draw this, I'm just gonna explain it real quick. If we have a point on the interior of a region, you can always draw a little neighborhood delta. A little, that just means a little neighborhood, okay? Just a little circle around it. And even if you get really super teeny close, you can still draw a little teeny circle around that. Does that make sense to you? You can define some points around it, which means that at that point that we can draw this neighborhood around, we can get to that point no matter what path. That means that we're continuous on that surface over that region, on boundary points. So if you're actually on there, you go, well, this looks pretty good, but these points out here don't look so hot. In that case, we say, you know what? We're going to restrict our paths. Just restrict our paths to all paths that come from the inside the neighborhood, like this. When we say paths outside, don't worry about those paths outside. So boundary points are okay as long as we restrict our paths. All this basically says, I know I'm going speeding through it because it matters. It does matter. But it's easier than some of these definitions make it. Here's what this says. If you have a region, you have a function that's defined over this region, it's going to be continuous at any point in that region. Why? Because you can roll a circle around it that's continuous within that circle. That's fine. On the boundary, you're still fine, because you can find some paths from inside the region that get there. In other words, all of this stuff says the following. A function is continuous at any point inside of its domain. That's all it says. Here's a domain. Here's a point. Continuous. Draw a little neighborhood around there. All the paths go to that point. No problem. Well, to get to that point, by any path, it's gonna be there's no jumps, there's no gaps, there's no asymptotes, there's nothing wrong in that if we're completely define that domain. Same thing on the boundary. There's no jumps or gaps within this part of it. We can find continuity there. All it says is that a function is continuous at any point inside the domain. That's what I want you to write down right now. So as far as continuity goes, a function is continuous at any point inside the region for which it's defined. Domain. Well, how do we define the regions? Well, how do we do that? On what regions are functions defined? We already did that. It's called the domain. Find the domain. You find out where the function is continuous. Do you remember that back from Calc 1 when you're like, wait a minute, finding continuity issues, remember the holes and asymptotes from Calc 1? You watch them on the videos, you probably saw that. But where we found discontinuities were exactly where we found domain issues. They were basically one and the same until we started restricting our domain. If we don't restrict the domain and continuity give you the same region. And that's what I'm saying here. I'm saying that a function is continuous at any point on the region for which it's defined. The region for which a function is defined to be the domain. This is this domain. And that's kind of beautiful, because we get a lot of the continuity properties we had before, they still work. All we have to look for are the same exact things we looked for before. Holes, these weird things that would be like denominators equal to 0, negatives inside square roots. So just look for the same problems we looked for domain. Does that make sense to y'all? Okay, there's a couple things I want you to write down here. A couple things that we get to use. The first one, polynomials are continuous everywhere. Rational functions are continuous everywhere the denominator is not 0. And continuity holds for compositions of continuous functions. So just put continuity holds for compositions. So those are the three things that I want you to put. Polynomials, continuous, everywhere. Rational functions are continuous everywhere where the denominator is not 0. Polynomials continuous everywhere. Rational functions continuous everywhere the denominator is not 0. And 3, continuity holds for compositions of continuous functions. This last statement is why I can't do the squeeze theorem until, like right now. We're going to do some continuity and then we'll talk about squeeze theorem, because this continuity holds for compositions of continuous functions. I need that to prove it. So we're going to do that in a little bit. Right now, I'd like to do one example, just one. Okay, by one I mean two. Two examples about continuity, then we'll take a break. We'll come back and maybe do one more. We'll do that squeeze theorem thing. I'll talk about compositions, and that'll be it. Pretty close. I do want some more energy out of you guys, though. You make me feel like I'm punishing you. Oh crap, you do feel like I'm punishing you. Question: Where would domain issues, and so likewise, where would continuity issues exist on this problem? If anywhere, where would they be? Good. Polynomial, continuous everywhere. Perfect. Polynomial, continuous everywhere. Rational function, continuous everywhere unless the denominator can equal 0. Now here's my question: Can the denominator equal 0?
No.
Do we have imaginary numbers? Thank goodness, no. So we don't even have those. So are there any continuity issues? So this would be continuous on, let's put it this way, on all points. Continuous on all ordered pairs, x, y.
Push for f of x, y.
Oh, yeah, I'm sorry. Thanks for that. I don't know if you're okay with that one. How about this? What if I just do one thing? Is that still continuous? So notice the change, please. Is that still continuous on all ordered pairs?
No.
What's the one point that I couldn't have?
0, 0.
0, 0. So this would be continuous, and here's how you write that. Write continuous on any ordered pair such that that ordered pair does not equal the point 0, 0. That's how we show the continuity. Say, hey, anything works. Only one that doesn't work is when the denominator is 0. That's a polynomial. It's 0, no problem. If it's 0, who cares? But this one can't equal 0. That only exists at one spot. That only exists when x, y equals the exact point 0, 0. That's my only discontinuity. Should your fans be okay with that one? Okay, here's the second example. Let me take a break. Please notice the compositions. Please notice that they're really not an issue as far as creating for you more discontinuities. All they do is they might have some within. So let's take a look at it. What do we know about this thing right now? Firstly, is e to the x continuous everywhere? E to the x is a function. That's continuous everywhere, for sure. Is x over y continuous everywhere?
No.
What's the problem here? What couldn't we have? Come on, quickly.
Y 0.
So we can't let y equal 0. So y cannot equal 0. Tell me right side something else quickly. What else do you know about this thing? Could it be 0? So that's it. That's literally it. The only things we have here are x got to be greater than or equal 0, y cannot be 0. So we have any ordered pair such that x must be positive and y cannot equal 0. Since domain gives you the region where your function is defined, and since the region where your function is defined, so it's going to be continuity, basically finding your domain is practically the same as finding your continuity in almost every single case. And that's what we deal with. We'll do maybe one more when we come back from a break, but I think we need a break here real quick. Show of hands feel okay with what we're doing so far. Okay. So a few examples. We're talking about continuity. What we're finding out is that finding continuity and finding the domain most of the time are pretty much one and the same. Huh, almost rhymes. I like that. So you're just looking for the problem issues. That's all we're doing. Now, that holds true for functions in 3 independent variables. So let's check out this domain. Here's the problem. Here, check out the continuity. Here's the issue. Just like domain of 2 variables is on a plane, 2D, domain of 1 variable is on a line, 1D, domain of 3 independent variables is 3D, which means continuity is also a 3D issue. So let's take a look at this. Do we have any domain issues on the numerator? Yes or no? Denominator? Yes or no? What do you know about denominators? Everybody, come on, quickly. So I know that that's true. That's it. That's the only continuity issue we have, so write it down. We want all sets of ordered triples such that x squared plus y squared plus z squared cannot equal 4 if you add 4 to both sides. I don't know if you're okay with that one. Now, think about what this means. Think about what this means. Can you tell me what shape, I'm going to ask you what shape this isn't. What shape is x squared plus y squared plus z squared equals 4? What shape is that? It's a what? What type of ellipsoid, since all of our numbers are exactly the same? It's a sphere. Here's what it says. It says any point in all of 3 space will work. We have no discontinuities there, except for this bubble of that sphere. All it says is that the points you can't plug in, all those points are on that sphere. Does that make sense to you? It's all of the 3D space. The discontinuity exists on that sphere. The points that create discontinuities are on that sphere. That's why we can't let it equal a radius of 2. So fans feel okay with that. That's it. That's all we're doing. It's just regular continuity. Now, what I do want to tell you, the statement 3 down here from a little while ago, continuity still holds for compositions, and parametrics are all compositions. So when we're going to try to figure out some continuity that has compositions in it, just remember one thing. You can't ever make domain or continuity issues better. You can only make them worse. That's encouraging, right? You can't fix a continuity issue, ever. Here's how to do some parametrics, some compositions, whatever you want to call them. Let's focus on finding h of xy such that this equals g of f of xy. In other words, what I want to do is, do you know how compositions work? This says take the f thing, put it in for the g thing. So take this entire thing and replace this variable and this with it. Do you actually want to do that? No, not really. All I'm worried about is what's the continuity going to be for this composed function that we're going to get. Here's how to do that. First, find the continuity here, and I'll show you how to work with it. What's the continuity?
All real.
Great. Why? But I don't want to say all real numbers, all ordered pairs. That's a better way to say it because these are ordered pairs. So this is continuous.
Hey, welcome to Draft Academy. My name is Mike. In this course, I'm going to be teaching you guys everything you need to know to get started in the C programming language. C is an awesome programming language, and it's actually one of the oldest programming languages around. In fact, a lot of modern programming languages are based off of C. So it's a really good idea if you want to get into C, or even if you're trying to get into something like C++, to learn the basics. And in this course, we're going to cover everything you need to know. I'm going to talk to you guys about installing a text editor and using the C compiler. And we're going to write some basic code. I'll talk to you guys about, what is a program and how do programs work and how does C read the instructions that you give it. And we're going to get into some more advanced stuff. We're going to look at things like if statements and loops. We're going to create different variables. We're going to talk about the different types of data that you can use in C. Then we're going to get more advanced. We're going to talk about things like structures and functions. We're going to talk about pointers. And basically, I'm just going to give you a full overview of all of the core concepts in C. So by the end of this course, you'll have a really good understanding and a really good foundation which you can build on. You can kind of go forward and learn some more. I'm really excited to be bringing you guys this basic course on C. I'm really excited for you guys to dive in and start using these tutorials. So feel free to click around through all the videos, and hopefully you'll learn something awesome about C. In this tutorial, I'm going to talk to you guys about getting everything set up to start programming in C. Now, in order to program in C, we're actually going to need two things. The first thing we're going to need is an environment where we can write our C programs. Now, there's a bunch of these different environments. Essentially, all you need is just a text editor. So anything that can allow you to write text and then save that text in a specific file format is going to work. Although, when we're working with C, a lot of times it can be useful to use a special environment called an IDE. An IDE stands for Integrated Development Environment. Basically, this is a special text editor which makes it a lot easier for us to write our C programs in. So I'm going to show you guys how to install an IDE called CodeBlocks. The second thing we need to write our C programs is going to be something called a C compiler. Now, C is a programming language, which means we can basically write out instructions that we want to give to the computer. But eventually, for the computer to be able to execute those instructions, they have to be compiled, which basically means like translated or transformed into a language that the computer can understand. So we're going to basically download and install a special program that will do that for us. So let's get started. I'm going to come over to my web browser, and I'm just going to go up to the Google search bar, and I'm going to search for a program called CodeBlocks. So just type in CodeBlocks C, and this link should come up. It's codeblocks.org. Now, this is an integrated development environment. It's basically a text editor that will make it really easy for us to write our C programs. So I'm going to come down here into downloads, and there's a bunch of options here. One says download the binary release, download the source code. In this tutorial, I'm going to talk to you guys about getting our first C file set up. So we're going to load up a C file, and we're going to be able to get everything working and test out our program. So I'm going to open up my CodeBlocks program, and this is the IDE that I'm going to be using for the rest of this course. So I'm just going to double click on it, and it should start opening. Once we have CodeBlocks open, you'll see over here there's a bunch of different options, like create a new project, open an existing project. So we're actually going to want to create a new project. So whenever we're going to start writing some C files, we're going to want to create a new project in CodeBlocks. So you can either click this button right here, or you can go up to File, New, and Project. So either way, it's going to bring you to this window over here. And there's going to be a bunch of options here. Basically, just these are different types of like C projects that we can create. What we're going to be doing is creating a console application. This is like just a basic C project that you could run on your computer. That's exactly what we need. So click on console application and click go. And I'm just going to click through this wizard, and you'll see over here it says C++ or C. Now, C and C++ are both different programming languages. For this course, we're going to be working with C, so just highlight C and click next. And we're going to give this a title. I'm just going to call mine draft. And we're going to have to put this project inside of a folder. So I'm going to open this up, and I'm just going to put this on my desktop. So let's click OK. And click next. And you can leave all of these options as the default, and we'll click finish. So now what we should have is our first C project in CodeBlocks. Now over here inside this little file explorer, you'll notice that draft is right here. So that was the name of the project that I just created. Down here we have this source folder, so I'm going to click down, and you'll see we have this file here called main.c. And this is a file that got automatically created for us by CodeBlocks. I'm just going to right click and open it, and you'll see over here we have some default code. So up here there's these little lines of code that say include. Down here this says int main. So this is the program that we're given by default when we created our C project, and this is sort of like the simplest C program that you can write. Essentially what this program does is it prints out hello world onto the screen. So in order to run this program and test it and just make sure that everything's working, I'm going to come up here, and you'll see that there's this green play button over here, and it just says run when I hover over it. When I click this button, this file that we have open right here, main.c, is going to get run. So we're essentially telling CodeBlocks to run this file and execute the program. So when I click the run button, we're getting this message that says the project hasn't been built yet. Do you want to build it? Click yes. And now over here, this little window pops up. Basically, this is the command prompt. So whenever I run a C program, this little window is going to pop up. So if I was to exit out of this and run this program again, you'll see this window pops up again. And it basically just executes the program. And in the case of this program, all we're doing is we're printing out hello world onto the screen. That's actually what this instruction does over here. When we open up this command prompt, it's essentially just executing the program, and it's printing out whatever we told it to print out. So it's printing out hello world over here. And printing something out onto the screen is really easy, and that's one instruction that we can give to the computer. But as we go through this course, we're going to learn all sorts of instructions that we can use. But the purpose of this tutorial was just to get our C project set up and to test our main.c file. So as long as everything works here, and you're good to go, and now we can start really learning how to program in C. In this tutorial, I'm going to talk to you guys about the basics of writing a program in C. So if you've been following along with the course, up to this point, we've installed a text editor, we've installed a C compiler, and we set up our first C program, our first C project inside of CodeBlocks. So now, essentially what we have is this file over here. This is that main.c file. I just kind of want to point out a couple things that are in here. First up here, we have these little instructions, which are just called include. And I'm not going to get too much into what those do in this tutorial. Later on in the course, we're going to talk about what these are actually doing and the specifics of how they're helping our program. But for now, just know that in order for us to use our program, we're going to need to have these guys up there. Next thing we have is this little block of code called main. And it just has this name main. You can see there's an open and closed parentheses. And this is actually what's called a method. And don't worry too much about what methods are. We're going to talk more about those in future. But essentially a method is just like a container where we can put some of our code. And this method main is very important because this is the method that's going to get executed when we run our program. So in C, we can actually write out a bunch of instructions for the computer, and then we can run our program. So we can tell the computer to execute those programs. And whenever the computer executes our C program, it's going to look inside of this main method. In other words, it's going to look inside of all the code inside of these open and closed curly brackets, and it's going to execute that code. So I have this instruction here. It's called printf. And basically, this is just printing out some text onto the screen. When we run our program, it's going to come into this main method, and it's going to execute all the instructions inside of here, namely this printf method. So if I was to run my program, then this is going to work. Now let's talk about actually running a program. Whenever whenever we want to run a program that we write in C, we actually have to do two things. First thing we have to do is what's called building a program or compiling a program. And basically what that does is it takes all of this C code and it translates it into a language that the computer is going to be able to understand and execute. So it's essentially taking this C program code, translating it into computer code, and then the computer can execute it and run our program. So the first thing we have to do is always build our C file. The second thing we have to do is run the file that gets built. So once we've built this program, we've compiled it down into code the computer can understand, we have to run it. Basically tell the computer to execute that code. And in Code Blocks, it's actually really easy to do this. So we can come over here and this little gear icon will allow us to build our program, and then this play button will allow us to run our program. But a lot of times when you're programming, you're going to want to build and run your code at the same time, right? You're just going to want to build it and run it just to see what happened, see how your program did. So we have this option over here called build and run, and this will both build your program and run it at the same time. So generally, as you're going through this course, you're going to want to be using this option, this build and run option. So when I click this, it'll essentially build my program, run it, and then it'll show up here on this little window. And this little window is basically a console window, you can call it. So a lot of people would refer to this as the console, and it'll just like output any information that we tell it to. So if we write a C program that doesn't output information, that doesn't print anything to the screen, then we wouldn't actually see this. But since we're using this printf command, that window is going to pop up. So let's talk about how these programs actually get executed. Essentially, when we write a program, we have a set of instructions. So when I'm writing a C program, I'm basically writing out a set of instructions. Imagine you were writing like a recipe or something, right? A recipe is essentially just a set of instructions that when executed correctly will result in, cooking or baking something delicious, right? And that's basically what these C programs are. It's a set of instructions that when executed correctly will result in the computer doing something for us. And one of the cool things about computers is that we can program them to do anything, and C is one of the best languages to do that with. So let's look at this instruction over here. It's called printf. And like I said, this prints something out onto the screen. You'll notice over here at the end we have this semicolon. And this semicolon is actually really important. So whenever we write an instruction in C, we always want to end it off with a semicolon. That tells C that we're done with that instruction and we want to move on to the next one. So I could actually copy this instruction and I could paste it down here. And now we're basically
Ever. Here's how to do some parametrics, some compositions, whatever you want to call them. Let's focus on finding h of xy such that this equals g of f of xy. In other words, what I want to do is, do you know how the composition works? This says take the f thing, put it in for the g thing. So take this entire thing and replace this variable and this with it. Do you actually want to do that? Not really. All I'm worried about is what's the continuity going to be for this compose function that we're going to get. Here's how to do that. First, find the continuity here, and I'll show you how to work with it. What's the continuity? Great. Why? But I don't want to say all real numbers, all ordered pairs. That's a better way to say it because these are ordered pairs. So this is continuous on all ordered pairs. True or false? This is continuous on all t. Yes or no? Okay, what's it not continuous at?
Multiply plus 0.
Say what?
Multiply is 20 plus 0 is 1.
No, plug in anything you want. Can you do it? Can you plug in anything to cosine? Can you plug in anything to sine? Can you plug in anything to t? No issues.
No.
Oops. Continuous on all t. Here's what I want to tell you. If this, please watch carefully what we're going to do. You're not watching, you should be watching. Please watch carefully. We're going to be taking this function and plugging it into this function. Does that make sense? Everything would be ending with x's and y's. The t's would disappear. That's what this says. Replace t's with xy stuff. You get me? So lots of xy's. If this is continuous everywhere, And this is continuous everywhere. Tell me where this is continuous. Everywhere. But we're going to be in terms of whatever that says. So h of xy, that's why it says xy, because you're going to do any xy's. This would be continuous also on all ordered pairs. Does that make sense to you, that track with you? Now let's try this one's a little more complicated. The first part's really easy. True or false, this is continuous on all xy, yes or no?
Yes.
True or false, this is continuous on all t, yes or no?
False.
Ooh. Continuous
No.
on t, such that, what?
Is that equal to 0 or positive?
Such that t is,
Positive.
let's make it really simple. This says greater than or equal to 0, this just takes away the equal. So that's okay with that one. Now, here's what's going on. When we find the continuity for h of xy such that this equals g of f of xy, what this says again, take your f function and plug it into your t function. Here's what that means. It means every place you have t, what are you going to have? You're not excited, you should be excited. Every place you got t, you're going to have what? No, you don't have xy. You're going to have an entire function. What entire function? This says, for every variable in this function, you're going to plug in this entire freaking function. There and there. Does that make sense? In other words, you're going to let t equal x minus 2y plus 3. Does that make sense to you? Now here's the magic part about that. What do you know about t? Read it. What do you know about t?
Must be
It's going to be greater than 0.
Yeah.
That means that t must be greater than 0. Therefore, this thing must be greater than 0. If you can see that substitution, then you got it made. Can you see how to get from here to here? T's going to equal this, right? Because we're going to take a function plugged in for t. If t has got to be greater than 0 by what we have, if t's got to be greater than 0, and t equals this thing, then this thing's got to be greater than or equal to 0. Why are we doing that in terms of x, y? Because the function's going to end in terms of x and y. Does that make sense? Now solve it. Do something. Just subtract the 3 or something. So we got x minus 2y is greater than, yeah, I flipped it around. X minus 2y is greater than negative 3. Does that make sense? So we found continuity. This will be continuous on all ordered pairs x, y, such that x minus 2y is greater than negative 3. So what we do is we figure out continuity. If it's all real numbers, great. All ordered pairs, I should say. Figure out continuity here. If it's not, just set the parameter equal to what you're plugging in for that parameter. And then you have this inequality. Solve for the inequality. And you have the domain and the continuity for that second composed function. Then not forget that one. Now, last one. This is going to be the opposite case. Let's start here. Is this continuous on all t? Yes or no? Is this continuous everywhere?
No.
This is tangent. Is it continuous on all x?
No. Yeah.
Continuous on all y? What's wrong with
No.
that? That's because all values of higher 2. So we have, this is continuous on ordered pairs x, y, such that x I don't care about. X is good, but I just can't have y equaling pi over 2. I can't have y equal pi over 2 or any multiple of that. So we're going to say plus k pi. And what that says is if you add or subtract pi to it, you still have a problem. Any multiple of k's integer, pi, you go, okay, so negative pi over 2, or 3 pi over 2, or any circle, any like half circle around there. You can't have any of those. No, here's the deal. Here's the deal. Watch carefully. If I want to talk about this, here's what I want you to see. This is going to be in terms of xy, correct? Is this going to add any more continuity issues to this situation?
No.
So this added, okay, this said I have continuity, so I didn't. So we have to set equal to this continuity, we have to figure it out. If I say I'm taking this whole thing, and I'm just going to substitute this in for t, this doesn't add any more problems. All it says is that, yeah, you're going to have continuity. Basically, the same region you had this. This was the only problem there. It was already in terms of x's and y's, so it's going to be this exact same value of points. Does that make sense to you? That the cosine's continuous everywhere. It's not making a difference for us. It's this piece that even when I put it here, I still can't have the y equaling those multiples of pi over 2. Do you guys catch that? So composing, you basically keep the same continuity. Sometimes you have to work with it and say, okay, well, my t's are changing to x and y's. Figure that out. But for the most part, you take continuity for both of them, kind of jam them together. That's basically what we're doing. So this says continuous everywhere. That means I'm not going to have any issues when I plug into this function. I'm not going to have any issues when I plug into this function. We look at this function. Okay, this is what I'm plugging into that. Where is this not continuous? Well, it's continuous everywhere except this. Therefore, since this doesn't create any more issues, this is also continuous everywhere except that. Should finish okay with that one. Okay, I promised you this. I promised that we were going to talk about the squeeze there. I'm going to show you one example. I said, you know, when we started this, it's really, really hard to prove that limits exist. It's really easy to prove they don't exist. We spend most of the time doing that. How we prove limits exist is by using continuity and just plugging in the number that uses continuity. We talked about that a little bit. We said if a function is defined, then it's got continuity. If it's got continuity, the limit exists. So just plug the number in. And if the function is defined there, then it's continuous there. We talked about the region. We talked about how if we're defined and we plug that point in over the defined region, then we find neighborhood points and we're continuous there. The limit has to exist. So if we're defined, continuity, no problem. Just plug the number, you got it. Well, what if we can't do that? And what if the limit still exists and we didn't have the magic trick of polar? This is the case that you use. So if we don't have that stuff, for example, let's talk about this limit, only one. First thing you should always do with limits is what? Plug it in. And you plug it in, you get 0 over 0, you can verify that formula if you want to. And we go, okay, we're used to saying things don't exist in this case, but this one does. How do you prove it? You might try polar and see what that gives you. You could try it. That might work, I don't know. I want to show you in this case how to use a squeeze theorem to your advantage. This is the other way. So the things we do with limits. First, plug it in. If you can plug it in and you get a number, then the function's defined there, which means we're continuous there. We just plug it in, we're good. If we're continuous, it exists. Got it. That's fantastic. Or we try to prove it doesn't exist by finding those different paths. We spend most of our time doing that. Or using the polar trick that we created. That was pretty cool. Or the squeeze theorem. Those are basically the things we do with limits. I'm going to show you the squeeze theorem right now. So let's take a look at this. Let's look at our function. And I want to consider the absolute value of the function. Where are you getting that from? I'll show you where. I'll show you where in a second. True or false? This denominator is always positive no matter what. The absolute value doesn't really matter. True or false? 5x squared is always positive no matter what. That doesn't really matter. True or false? Y is positive no matter what. False. So this would equal 5x squared over x squared plus y squared, absolute value of y. Does that make sense to you? Now we're going to build some stuff here. I don't want to confuse you, but we're going to build from scratch and try to get back to this thing. Try to get here. So here we go. First, plug it in. If you can plug it in and you get an uptick that we created, that was pretty cool. Or the squeeze theorem. Those are basically the things we do with limits. I'm going to show you the squeeze theorem right now. So let's take a look at this. Let's look at our function. And I want to consider the absolute value of the function. Where are you getting that from? I'll show you where. I'll show you where in a second. True or false? This denominator is always positive no matter what. The absolute value doesn't really matter. True or false? 5x squared is always positive no matter what. That doesn't really matter. True or false? Y is positive no matter what. False. So this would equal 5x squared over x squared plus y squared, absolute value of y. Does that make sense to you? Now we're going to build some stuff here. I don't want to confuse you, but we're going to build from scratch and try to get back to this thing. Try to get here. So here we go. This is going to seem kind of nonsense, but you understand this, right? That this is equal to 5. 5x squared plus x squared is equal to 5. You go, okay, well, why are we doing that? Well, that implies this. If I add anything to the denominator, if this equals 5, and I add something that's greater than or equal to 0 here, is it still equal to 5? What would it be? Smaller than, or if it's 0, it would be equal to 5. Does that make sense? True or false? Y squared is greater than or equal to 0. So since y squared is greater than or equal to 0, if this equals 5, and I add something to the denominator, I make the denominator bigger, I make the fraction smaller, it's got to be less than 5, or at most equal to 5. Head nod if you're okay with that one. Okay, we're going to use it in a second. Now, this is why we have to have the absolute value. You know I can do anything I want to with inequalities as long as I do it to both sides, and if I multiply by a negative, I got to have to equal to 5. Head nod if you're okay with 5. Does that make sense? True or false? Y is equal to 5. What would it be? Smaller than, or if it's 0, it would be equal to 5. Does that make sense? True or false? Y squared is greater than or equal to 0. So since y squared is greater than or equal to 0, if this equals 5, and I add something to the denominator, I make the denominator bigger, I make the fraction smaller, it's got to be less than 5, or at most equal to 5. Head nod if you're okay with that one. Okay, we're going to use that in a second. Now, this is why we have to have the absolute value. You know I can do anything I want to with inequalities as long as I do it to both sides, and if I multiply by a negative, I got to flip them, right? Do you know that? I'm going to multiply by y. Now that's a problem. It's a problem if I do that. What's the problem? If I multiply by just times this by y and times this by y, that's a problem. Because y could be positive, y could be negative, I would know, I would have a correct inequality, that would be a big situation. Does that make sense? However, if I force this thing to be absolute value, now I'm multiplying by what type of number? For sure positive. Do I have to flip to be the inequalities? No. Okay, what it gives us is 5x squared, absolute value, oh my gosh, over x squared plus y squared is less than or equal to 5 absolute value y. Can I have an honest show of hands if you feel okay with this so far? This is the reason why we needed the absolute value, was so that I could multiply by something and not flip that inequality and get the same thing out of it. Do you guys get the idea? That's why I needed that. Now, let's think about this. Tell me something. We're going to start with this. Tell me something about... Tell me one thing about that you know. It's on the board already. Tell me one thing about that you know.
Always positive?
It is always positive. So it's greater than 0. Tell me the other thing that we just found out. Say that again. How the squeeze theorem works is this. It says if you take the limit of this, and you take the limit of this, and they give the same number, the thing squeeze or sandwich theorem, some people call it, the thing sandwich or squeeze between them has to be the same value. What's the limit of 0 as x, y approaches? I don't even care. Come on, it's not your question. What is it? And what's the limit of 5 absolute value of y as x, y approaches 0, 0? Notice there's no x, I don't even care. What's it go to?
0.
By the squeeze theorem, since the limit of this function goes to 0, and the limit of this function goes to 0, the limit of this function
This is 0.
by the squeeze theorem. 0. We built it. 0, 0, 0, 0.
0.
Now, we haven't proved the darn thing right now, but we're about to. You guys okay with this? You sure? No?
Yes.
I want you to look back at this piece. This piece is equal to that piece. Do you guys follow that? Yeah, no? Therefore, the limit of the absolute value of all this junk is 0. And you also, but wait, Leonard. Wait, Bill Leonard. Is this exactly the same as that?
Yeah.
Nope.
No.
No. But this is why we had statement number 3 over here like 25 minutes ago. It was this. Continuity holds for compositions. of continuous functions. Here's my question to you. Is the absolute value function a continuous function?
Yes.
Do you see that this is a composition of this crappy function inside the absolute value function? Do you guys see that? Continuity holds. That means we can do this stuff with it. It means that the big point here says that means that this limit equals the absolute value of the limit of 5x squared y, x squared plus y squared. X, y, 0, 0, 0. Awesome. That's the same thing. Absolute value of 0 is 0. We get the same exact thing. So we have this composition of continuous functions. We prove that limit exists by the squeeze theorem. I got to stop it right here, and then we're going to call it good on this section.
Going to be executing this instruction twice. So if I was to run and build my program, you'll see that we're not only printing it out once, but we're also printing it out twice. So when we run our program, the program comes down into this main method, and it looks at all the instructions inside of it. So it starts with this first instruction, it executes it, right? So it prints out hello world onto the screen, and then it also prints out a new line. So this \n is like a new line character, and that'll move the text onto a new line. When it's done with this instruction, it moves on to the next instruction, and it'll execute that instruction. So as we go forward and we learn how to write in C, we're going to learn more and more complex instructions. And we'll be able to use all those instructions in conjunction with each other to specify some seriously complex programs. But for now, this is really the only instruction that we know, which is printf. So why don't we use this printf instruction in order to draw out a little shape onto the screen? So I'm going to show you guys how we can draw out like a little triangle onto the screen. I'm going to take this printf, and I'm actually just going to get rid of hello world, and I'm going to copy this a couple times. So I'm just going to copy it, and we'll paste it down here, maybe 4 times. And what I can do is I can specify instructions to the computer that will tell it to draw out a particular shape. So down here I can make like a /, and over here we'll make another one, and I'll make another one, and I'll make another one. And you can see here I've drawn like a little diagonal line with these /. Now I'm going to draw vertical bars going all the way down. So I'm going to put one here, I'm going to put one here, put one here, and finally, why don't we draw some underscores, and then we'll put one. So I'm basically drawing out a little triangle shape. And these \n's are just printing out a new line. So anytime I print this, it's going to move it onto a new line. So it'll print this guy out now on the line down, the line below. So if I was to save my program and execute it, now the computer's going to go through, it's going to execute each one of these instructions in order, and we'll be able to print out the shape onto the screen. So let's do that. You'll see over here we get our shape. And one thing I really want to stress is that order matters. So if I took this instruction and I placed it up here as the first instruction, now this is going to get printed out first. So when I run my program, you'll see that we're printing out this kind of funky looking shape. And that's because we changed up the order of the instructions, so the computer changed the order in which it executed those instructions. And you'll notice here again, we're using this semicolon after each line of code. So that's kind of the basics of writing a program. That's essentially all you need to know. When we're writing a program, we're specifying a list of instructions that we want the computer to carry out, and depending on which instructions we give the computer and which order we give them and how complex the instructions are, that'll determine what the program does. And as we go through this course, we're going to learn more and more complex instructions. We're also going to learn how we can take simple instructions like printf and do different things with them to make our programs a lot more powerful. In this tutorial, I want to talk to you guys about variables in C. Now, when we're using C programming language, a lot of times we're going to be dealing with data. So there's going to be different data values or different information that we're going to want to keep track of and use inside of our programs. And sometimes it can be difficult to maintain and keep track of all that data. And that's where variables come in. A variable is essentially a container where we can store different pieces of information. So different data values, we can store things like numbers or text or characters. And these variables make it a lot easier for us to keep track of and manage all the data in our program. So I'm going to show you guys basically how variables can be useful and how we can use them in our C programs. And down here, I have a very basic program. I'm basically just printing out a little story. It says, there once was a man named George. He was 70 years old. He really liked the name George, but did not like being 70. So this is a simple program. We're just printing out a bunch of different lines of text. And then when I run this program, you'll see we print out the actual story. So over here, we have our story. And this is great. But let's say that I'm reading through my story, I'm reading through my program, and I'm thinking to myself, I think I want to change the character's name. So instead of calling the character George, why don't we call him like John? In order to make that change, I'm going to have to look through my entire program and find every place where we mention the character's name. So right here is one, change it to John. I'm going to have to keep looking, and here's another one, so we'll change this to John, right? So I have to manually go through and change every instance of the character's name to John. And let's say that, okay, that sounds pretty good, but maybe I'm thinking I want to make the character a little bit younger. So instead of 70, why don't we make him 35? So now again, I'm going to have to look through my entire program, find every place where we mention the character's age, and change it to 35. So there and there. There you go. I changed the program, I updated it, I modified it. Now if I was to run this program, then all that information will be updated and we'll have our new story. Here's the problem though. I'm dealing with a very short story. I mean, this is 4 lines. We only mentioned the character's age and name twice. But imagine if I was writing out a huge C program that had hundreds of lines in this story. So this story had hundreds of lines. Maybe we mentioned the character's name hundreds of times. We mentioned their age hundreds of times. Well, if I wanted to change the character's age or name, I would have to go through and manually change it in every single location. And that would take forever and it would be a huge drag. Basically, that's not a good way for us to manage and maintain the data in our programs. Right? We basically have 2 pieces of data that we're working with consistently in this program, the character's age and the character's name. What I want to show you guys now is how we can use variables to better keep track of and manage these pieces of information. So remember, a variable is basically just a container where we can store some data. So I'm going to create 2 variables which will store the character's name and the character's age. And I'll show you guys how this can make our program a lot easier to manage. Up here above these print statements, I'm just going to make a new line, and I'm going to come over here, and I want to create a variable. Now, whenever we create a variable in C, we have to give C a couple pieces of information. So we have to basically tell C a couple different things. The first thing I have to tell C is what type of information we want this variable to store. Now I'm going to get into different data types that we can represent in C more in the next tutorial, but for now just know that there's a bunch of different types of data that we can store in C. We can store things like numbers, characters, we can store text, we can store decimal numbers, all sorts of stuff like that. In our case, I'm going to store the character's name. And the character's name is basically just a collection of characters. So in order to create this variable, the first thing I have to do is tell C that I want to create a variable that's going to store characters. So to do that, I'm just going to type out char, just like that. And now basically tell C, hey, we're going to store characters inside of this variable. After we type out char, I want to type out the name of the variable that I want to create. Remember, a variable is a container, and it's a good idea to give these containers descriptive names. And those names will basically let us know what that variable is storing inside of it. So I'm going to call this character name. And now what I want to do is I basically want to store multiple characters. So over here I'm telling C that I want to store a character, but in C we can also store, instead of just storing like one single character, we can store a bunch of characters. And that would be kind of like, a name. So there's like 4 characters in here. In order to store a bunch of characters inside this variable, after we type the variable's name, we're going to have to make an open and closed square bracket. And that's going to tell C that we want to store a bunch of characters inside this variable. So I'm going to type char character name, open closed square brackets. I'm going to set this equal to something. So I'm essentially assigning a value to this variable. And I'm just going to make open and closed quotation marks. And inside here we're going to type out the value that we want to store. So in my case, I'm just going to store the character's name, which is John. And then as always in C, we're going to have to end this off with a semicolon. All right, so essentially what I did here was I created a variable, and I told C what I wanted to store in the variable. I wanted to store a character. I gave this variable a name. It was character name. And I used these open and closed square things like numbers, characters, we can store text, we can store decimal numbers, all sorts of stuff like that. In our case, I'm going to store the character's name. And the character's name is basically just a collection of characters. So in order to create this variable, the first thing I have to do is tell C that I want to create a variable that's going to store characters. So to do that, I'm just going to type out char, just like that. And now basically tell C, hey, we're going to store characters inside of this variable. After we type out char, I want to type out the name of the variable that I want to create. Remember, a variable is a container, and it's a good idea to give these containers descriptive names. And those names will basically let us know what that variable is storing inside of it. So I'm going to call this character name. And now what I want to do is I basically want to store multiple characters. So over here I'm telling C that I want to store a character, but in C we can also store, instead of just storing like one single character, we can store a bunch of characters. And that would be kind of like, you know, a name. So there's like 4 characters in here. In order to store a bunch of characters inside of this variable, after we type the variable's name, we're going to have to make an open and closed square bracket. And that's going to tell C that we want to store a bunch of characters inside this variable. So I'm going to type char character name, open and close square brackets. I'm going to set this equal to something. So I'm essentially assigning a value to this variable. And I'm just going to make an open and closed quotation marks. And inside here we're going to type out the value that we want to store. So in my case, I'm just going to store the character's name, which is John. And then as always in C, we're going to have to end this off with a semicolon. All right, so essentially what I did here was I created a variable, and I told C what I wanted to store in the variable. I wanted to store a character. I gave this variable a name, it was character name, and I used these open and closed square brackets to tell C that I wanted to store a bunch of characters, not just one. Now what we can do is we can make another variable to store the character's age. So in this case, we're going to want to do something similar, but we're going to want to store a number. There's a bunch of different ways that we can store numbers in C, but for our purposes, we're storing a name, so we're going to use something called an integer. And an integer is basically just a whole number. So I'm just going to type out int, and that basically stands for integer, and now we're going to give this a name, so I'm going to call this character age, and I'm going to set this equal to a number. So in our story, the character is 35, so I'm just going to type out 35, and now we can again end this off with a semicolon. So I have 2 variables here. This one's storing a collection of characters, this one's storing an integer. Now the question becomes, how can we use these inside of our program? Well, basically what we can do is we can print them out alongside of this text, and we can actually use this printf instruction in order to do that. So I'm going to show you guys how to do this, and then we're going to talk about it. So basically, I'm going to go over here where we have the character's name. I'm going to erase this, and I'm going to replace it with a % sign and an s. And now over here, I'm going to make a comma, and I'm just going to type in the variable name. So I'm going to type in character name. And basically what's happening is when we use this %s, we're telling C that inside of this string of text here, we're going to want to insert another string. And a string is basically just a collection of characters. So I could call this up here a string variable. So when I say %s, this is basically a placeholder. And I'm telling C, I'm going to insert a string into here. And over here, I use this comma, and I type out the string that I want to include. So in our case, it's character name. And so basically over here, it's going to say there once was a man named %s, and it's going to replace %s with whatever we specify over here. So it's going to replace %s with the value that's stored inside that character name variable. So I'm going to save this and we'll run our program. And now you'll see that it's still printing out there once was a man named John, even though we didn't actually type out John over here, we just typed %s in the character name. So I can do this in this other spot too. So down here, we're also using the character name. So I can type %s, and over here, we can type character name. And again, this is going to act as a placeholder for this string of characters that we specify over here. Let's do the same thing with the age. So over here we have the age is 35. I'm going to do something similar. I'm going to say percent, but now because I have a number, instead of using %s, I'm going to use %d. And that basically means that we're going to insert an integer number into here. So I'm saying he was %d years old. And over here I'm going to make a comma, and I'm just going to type out the name of the variable that I want to be placed inside of here. So I'm just going to be character age, and we're going to do this one more time down here. I'm going to type %d and character age. So essentially what I'm doing is I'm printing out the value that's inside of character age where I specify this placeholder. So let's go ahead and run our program, and now you'll see it's going to look exactly the same as it did before. It's the same story, the same name, and the same age, except I didn't have to actually type out the character's age and the character's name inside the story. I just referred to the variable. And what's cool about variables is I can come up here, and let's say I wanted to modify the character's age. All I would have to do is modify it in this one spot. So we can change the character's name to like Tom, and we can also change their age to like 67. And now when I run my program, all of that's going to get updated in the story. So now it's using the name Tom and the age of 67. In our case, we only mentioned the character's name and the character's age a couple times, but you can imagine if I was mentioning this variable like 10 or 20 or 30 times, having to change it in each one of those individual spots would be extremely difficult. So variables are great because we can store the value one time, and if we want to modify it, we just modify it in one place. So another cool thing we can do with these variables is we can actually modify them. So let's say that halfway through the story, I wanted to change the character's age. I can actually come down here, I can make a new line, and right above these print statements, I could give this variable a new value. So I could say character age, and I can set it equal to something else. So we can set it equal to like 30. And again, we want to include that semicolon. So now halfway through the story, the character's age is actually going to change. So you'll see it says there once was a man named Tom, he was 67, and then down here the age is being 30. So we actually modified the value that was stored inside of the variable halfway through printing out our story. And that's really why variables are useful. So that's kind of a basic overview, introduction into what variables are, why they're useful, how we can use them. And over here again, we're storing a collection of characters, which is called a string, and we're also storing this integer. But there's some other data types that we can also represent. So in addition to representing like a string or a number, we can do some other stuff as well. I'm going to talk about that in the next video. But for now, this has been a basic overview, introduction into variables in C.
In this video, we're going to talk about how to find the partial derivative with respect to a certain variable. So for example, let's say if we have a function that consists of multiple variables, in this case x and y, and let's say it's equal to 7x squared minus x cubed y to the fourth plus 5x to the fourth y cubed. So what is the partial derivative of this function with respect to x? How can we find the answer? The partial derivative with respect to x is symbolized by the variable f sub x. Now in order to find it, every other variable, in this case y, you need to treat it as a constant. You only treat x as a variable. Everything else, you view it as a constant. Now before we do this problem, let's review the power rule. Let's say if we have a function x to the n. If we wish to find the derivative, it's going to be n x raised to the n minus 1. So for example, the derivative of x to the fourth is 4x cubed. The derivative of x cubed is 3x squared. The derivative of x to the fifth is 5x to the fourth. The derivative of x squared is 2x to the first power. The derivative of x, or x to the first power, is 1x to the 0, which is the same as 1. So what is the derivative of x squared? The derivative of x squared is 2x. Now what about the derivative of x cubed? We know it's 3x squared. Now y, we're going to treat it as a constant, so we're just going to rewrite it. The derivative of x to the fourth is 4x cubed. And then we won't change the y to the third. So that's how you can find the first derivative, the first partial derivative with respect to x. Treat x as a variable, and any other variable treat it as a constant. So this is equal to 14x minus 3x squared, y to the fourth, plus 20x cubed, y to the third. So that's the answer. That's the first partial derivative with respect to x. Now what about the partial derivative with respect to y? What is the answer in that case? So 7x squared is treated as a constant. The derivative of a constant is 0. The derivative of y to the fourth is 4y cubed, and the derivative of y to the third is 3y squared. So in this case, we need to treat x as if it's a constant. So this is going to be negative 4x cubed y cubed plus 15x to the fourth y squared. So that's the partial derivative with respect to y. Let's try another example for the sake of practice. Let's say z is equal to 3x squared y to the fourth minus 5x to the seventh plus 4y to the eighth. Find the first partial derivative with respect to x and with respect to y. So if you see z is basically a function of x and y. So you can write it as f of x comma y or just z, it doesn't matter. Now the first derivative with respect to x is going to be, so keep in mind, let's treat y as a constant. So differentiate only the x variables. The derivative of x squared is 2x. And the derivative of x to the seventh is 7x to the 6th. Now, in the last term, there is no x variable. So 4y to the 8 is treated as a constant, and the derivative of any constant is 0. So this is going to be 6x, y to the fourth, minus 35x to the 6th. So that's the first partial derivative with respect to x. Now let's find it with respect to y. So let's treat x as a constant. So the derivative of y to the fourth is 4y cubed. 5x to the seventh is a constant, so that's going to become 0. And the derivative of y to the 8 is 8y to the seventh. 3 times 4 is 12, and 4 times 8 is 32. So this is the answer. That's the partial derivative with respect to y. Now let's work on an exponential function. Let's say z is equal to e raised to the x squared times y cubed. What is dz dx and dz dy? So as we recall, z is the same as f of x comma y. So dz dx is the partial derivative with respect to x. That's the same as f sub x. And dz dy is the partial derivative of the function z with respect to y, which is the same as fy. So if you see those symbols, you know what they mean. So now, let's talk about the derivative of an exponential function. The derivative of e to u is equal to e to u times u prime. So let's say if you want to find the derivative of e to the x cubed, it's going to be the same thing, e to the x cubed times the derivative of x cubed, which is 3x squared. So if you want to find the derivative of e to negative 5x, it's going to be e to negative 5x times negative 5. And e to the x is going to be the same thing times the derivative of x, which is 1. So I'm going to give you some examples so you know how to use this formula. Now let's apply that to the problem that we have. Let's just get rid of this portion. Let's keep the formula there. So let's find dz dx. So it's going to be e to u, which is e to the x squared y cubed. It's going to be the original expression times the derivative of x squared y cubed. Now we're going to find a partial derivative. That means we're going to treat y as a constant. So we're going to differentiate x squared, which is 2x, and rewrite y cubed. And that will be it. We don't have to use a product rule here. We're just only differentiating the x variable. And so that's it. It's going to be 2x y cubed times e raised to the x squared y cubed. Now let's find dz dy. So if z is equal to e x squared y cubed, let's differentiate both sides with respect to y. So you can represent it using symbol d over dy. So on the left we're going to have dz dy, and on the right it's going to be the same thing, e to u, which is e to the x squared y cubed times the derivative of x squared y cubed. So we're going to treat x squared as a constant. So we're going to rewrite it and multiply by the derivative of y cubed, which is 3y squared. So the answer is 3x squared y squared e to the x squared y cubed. So that's dz dy, which is the same as f sub y. So here's the problem that you try to practice. Let's say z is equal to x to the fourth, e raised to the y to the fifth. Find the first partial derivative with respect to x and with respect to y. So go ahead, take a minute, and pause the video. So let's find dz dx. So notice that x to the fourth is a variable, and e y to the fifth is a constant because it doesn't have an x variable. It only has a y variable. So we're going to differentiate x to the fourth, which is 4x cubed, and then simply rewrite the constant. So that's dz dx. Now dz dy, x to the fourth is not a constant, so we're just going to rewrite it. And then differentiate e y to the fifth. So using this formula, it's going to be the same thing, e raised to y to the fifth times the derivative of y to the fifth, which is 5y to the fourth. And so these are the two answers. Now let's say that f of x comma y is equal to the y to the fifth, which is 5y to the fourth. And so these are the two answers. Now let's say that f of x comma y is equal to the natural log of x squared plus y squared. Go ahead and find f of x, the partial derivative with respect to x, and fy. So first, you need to know how to differentiate natural log functions. The derivative of ln u is equal to u prime divided by u. So for example, if we want to find the derivative of ln x squared plus 8, it's going to be the derivative of x squared plus 8, which is 2x, divided by whatever stuff is on the inside of the natural log function, which is x squared plus 8. So let's say if we want to find the derivative of x cubed, ln x cubed plus 5x minus 9, it's going to be the derivative of the inside function, which is 3x squared plus 5, divided by the original of the inside function. So for example, if you want to find the derivative of ln x, it's going to be the derivative of x, which is 1, divided by the original stuff on the inside, which is x, so you get 1 of x. So now let's solve the problem that we have. Let's find f of x. So it's going to be the derivative of the stuff inside. That is the derivative of x squared plus y squared. The derivative of x squared is 2x. And y squared we're going to treat as a constant because we're trying to find the partial derivative with respect to x. So y squared is 0, divided by the original x squared plus y squared. So it's simply 2x over x squared plus y squared. Now if you want to find f sub y, it's going to be the derivative of y squared, which is 2y. X squared is a constant, so that becomes 0, divided by the original x squared plus y squared. So this is the first partial derivative with respect to y, and this is the first partial derivative with respect to x. Here's one you try. It might be a little challenging, but go ahead and try. Let's say z is the natural log of x squared divided by y. Go ahead and find dz dx and dz dy. So the derivative of the natural log of u, we know it's u prime over u. So u is basically the function on the inside, which is x squared divided by y, which I'm going to write as x squared times 1 over y. So now what's u prime? It all depends on if we're looking for dz dx or dz dy. Let's find dz dx first. So u prime, which I'm going to write as u prime with respect to x. We're going to treat x as a variable. So the derivative of x squared is 2x times the constant 1 over y. We're going to treat 1 over y as a constant. So now dz dx is going to be the same as u prime over u. U prime is 2x times 1 over y divided by u, which is x squared times 1 over y. So we can cancel 1 over y, and we can cancel an x. So we're left over with 2 divided by x. So that's the answer for the partial derivative with respect to x. Now let's find it with respect to y. So let's find u prime with respect to y. So x squared is going to be treated as constant times something, right? Now whenever y is y to minus 1, and the derivative of y to minus 1 is negative 1, y to minus 2. So u prime with respect to y is negative x squared times 1 over y squared. So we can write that. So using this formula, u prime of u, dz dy is going to be u prime, which is negative x squared times 1 over y squared, divided by division of u value, which is x squared times 1 over y. So we can get rid of the x squared term, and let's multiply the top and the bottom by y squared to simplify the complex fraction. So these will cancel. So on top, we're just going to have negative 1. On the bottom, y squared divided by y is y. So this is the first partial derivative with respect to y. It's negative 1 over y. Now let's try a problem involving square roots. So let's say f is equal to the square root of x squared plus y squared. Find the partial derivative with respect to x and y. So first, let's rewrite it. So this is equal to x squared plus y squared raised to 1 half. So let's find the partial derivative with respect to x. So we need to bring 1 half to the front. Or we're going to keep everything on the inside the same. So basically, we need to change the speed. Now 1 half minus 1, that's negative 1 half. And now we need to find the derivative of the inside function with respect to x. The derivative of x squared is 2x. And for y squared, we can treat that as constant, so that's 0. 1 half times 2 is 1. So therefore, the final answer, you can also bring this down because it's negative 1 half. So the final answer is going to be x on top divided by x squared plus y squared raised to positive 1 half. When we move from the top to the bottom, the exponent will change sign. It's going to change from negative to positive. So we need to bring 1 half to the front. Or we're going to keep everything on the inside the same. So basically, we need to change the speed. Now 1 half minus 1, that's negative 1 half. And now we need to find the derivative of the inside function with respect to x. The derivative of x squared is 2x. And for y squared, we can treat that as constant, so that's 0. 1 half times 2 is 1. So therefore, the final answer, you can also bring this down because it's negative 1 half. So the final answer is going to be x on top divided by x squared plus y squared raised to positive 1 half. When we move from the top to the bottom, the exponent will change sign. It's going to change from negative to positive. So you can write the final answer as x divided by the square root of x squared plus y squared. So that's the first partial derivative with respect to x. Now what about with respect to y? So we're going to take the exponent, move to the front, and keep the inside the same, and then subtract 1 half by 1, which will give us negative half again. And now we need to differentiate the inside function. X squared will now be treated as constant, so that's 0, and y squared is 2y. So as you can see, everything's going to be the same, but we're going to have a y variable on top instead of an x variable. So this is the final answer. It's y over the square root of x squared plus y squared. Now let's try a straight function. Let's say z is equal to sine x cubed y to the fifth. Find dz x and dz y. So if you want to find the derivative of a sine function, the derivative of sine u is cosine u times u prime. So if we want to differentiate sine x squared, it's going to be cosine x squared times the derivative of the inside part. The derivative of x squared is 2x. So let's say you have sine x to the fifth. It's going to be cosine x to the fifth times the derivative of x to the fifth, which is 5x to the fourth. So now let's work on the problem that we have. So let's find dz dx. The derivative of sine is cosine, and wherever it is inside sine, we're going to keep the same. We're not going to change it. So it's going to be x cubed y to the fifth. And now we need to differentiate x cubed y to the fifth with respect to x. So we're going to treat x as a variable, y is constant. The derivative of x cubed is 3x squared, and then we're going to multiply that constant. So that's the answer, which we can write as 3x squared y to the fifth. And then cosine x cubed y to the fifth. Now let's find dz dy. So it's going to be cosine x cubed y to the fifth. First part is not going to change, but the second part will. Now x cubed is the constant, y to the fifth is the variable. So we can rewrite the constant times the derivative of y to the fifth, which is 5y to the fourth. So that's 5x cubed y to the fourth times cosine x cubed y to the fifth. And so that's going to be the answer. Now let's say if we're given a function f of x comma y, which is 2x cubed y squared plus 5y cubed plus 4x squared. And we need to evaluate f of x and f of y at the point 1 comma 2. How can we do so? Well, first let's find the partial derivative. With respect to x, it's going to be the derivative of x cubed, which is 3x squared. We're going to treat y squared as a constant. The derivative of this constant becomes 0, so we ignore it. And the derivative of 4x squared is 8x. So now
in this tutorial, I want to talk to you guys about data types in C. And in the C programming language, we're going to be dealing with a lot of data. So generally, when you're writing programs, you're going to be dealing with all sorts of information. And in this tutorial, I just want to talk to you guys about what types of information we can represent and use inside of our C program. These are called data types. Right? So what are the different types of data that we can work with in our program? So I'm going to show you guys all those different data types right now. So a lot of times in C, when we're working with data, we're going to be storing that data inside of variables. So I'm just going to show you guys a bunch of different variables that we can create and all the different types of data that we can store inside of those variables. So remember, whenever we create a variable in C, we have to tell C a couple pieces of information. And the first piece of information we need to tell C is what type of data that we want to store inside of that container, inside of that variable. So let's talk about the different types of data. One of the most basic types of data, and probably one of the types of data you're going to be using the most, is going to be numbers. There's actually two very important types of numbers that we can represent in C. So the first type is called an integer. And an integer is basically a whole number, so it's a counting number, right? If I was counting on my fingers 1, 2, 3, 4, 5, I'm just counting out whole numbers. And I'm not saying like 1, 1 half, 2, 2.3. Like I'm counting whole numbers, and that's what an integer is. So to create an integer, we can just say int, and we'll give this a name. So we can say like age, and we can set age equal to like 40 or something. Now, whenever we want to use an integer in C, we always just want to type out the number. So you'll notice I'm not putting quotation marks or parentheses or anything around this. I'm just typing out the number like that. And now we actually have our variable age. Another type of number we can create is a decimal number. So this would be a number unlike an integer. So it would be like 2.5 or 8.67 or 7.538, right? So a number that has a decimal point associated to it. So there's actually two types of decimal numbers in C. There's something called a double, and there's something called a float. And I'm not going to get too much into the difference between the two of them. But as a beginner to C, for the most part, you're just going to want to use a double. So I'm just going to type out double, and this could be like someone's GPA, for example, might be like 8. I'm not going to get too much into the difference between the two of them. The decimal point associated is a decimal number. So this would be around this. I'm just typing out the number like that. And now we actually have our variable age. Another type of number we can create is a decimal number. So this would be a number unlike an integer. So it would be like 2.5 or 8.67 or 7.538, right? So a number that has a decimal point associated to it. So there's actually two types of decimal numbers in C. There's something called a double, and there's something called a float. And I'm not going to get too much into the difference between the two of them. But as a beginner to C, for the most part, you're just going to want to use a double. So I'm just going to type out double, and this could be like someone's GPA, for example, might be like a 3.7 or whatever. So you can use the double to represent decimal numbers. It's also important to note that I can also represent like the number 3. So I can just say like 3.0, and that's going to be a decimal. Or I could say 40.0. So the difference between 40 and 40.0 is that 40.0 is a double, it's a decimal number, and 40 without decimal point is an integer. So that's something just to keep in mind. So you can make this like 3.6. So those are the two basic types of numbers, integers and doubles, and those are going to come in handy all the time. Now, the next type of data that we're going to want to store is going to be characters. So in C, we can store single characters inside of a variable. So I can just say char, and that stands for character, and we can give this a value, so maybe it'd be like someone's grade. And when we create a character in C, we're basically going to specify the character that we want to store inside of single quotation marks. So inside of these single quotation marks, I can put a letter. I can put like A, or lowercase a, we can put H, C, D, F. Basically, you can put any character that you want to store. So if I put an A here, now this character variable grade is going to store the single character A inside of it. It's important to know that you can only store one character. So I couldn't put like a whole bunch of characters over here. That's actually going to throw an error. All we can do is store one single character. But these three are the basic data types in C. So these are the basic types of information that we can deal with in our C programs. And just using these three data types, we can represent all sorts of information. I also want to talk to you guys about one sort of extra data type, and it's not technically a data type in C. It's technically like a modification of the character data type. So you notice when we create a character, we can only store one letter, one single character inside of it. But a lot of times we're going to want to represent more than one character. So we're going to want to represent like a string of characters, and generally this is called a string. So it's a collection of characters that are grouped together. And we can use this char data type in order to create a string. So I can basically say char, I can type out the name of the string that I want to create, so I can say like phrase, and then after this I can make an open and closed square brackets. And this is basically going to tell C that we want to string a bunch of characters together. And what we're actually doing is creating something called an array, and I'm going to get into arrays later in the course, but just for now know that we can create a string of characters by using char, specifying the name, these open and closed square brackets, and then we can create this using two open and closed quotation marks. So instead of these single quotes up here, we're just going to use double quotes, and I can type in like
now we can plug in point 1, 2. 2 times 3 is 6, times 1 squared, times 2 squared, and we have 8 times 1. So 2 squared is 4, times 6, that's 24. Plus 8, so that's 32. So that's the value of the first derivative with respect to x at the point 1, 2. Now let's do the same for fy. So first we define it. Let's treat x as a constant. The derivative of y squared is 2y, and the derivative of y cubed is 3y squared. And 4x squared is constant, so that becomes 0. Now let's plug in point 1, 2. 5 times 3 is 15. So then we have 2 times 2 times 2, which is 8. 2 squared is 4 times 15, that's 60. 8 plus 60 is 68. And so that's all you need to do in order to evaluate the derivative at the point. Find the derivative and plug in the x and y values. Here's another example, but this one might be more trivial. Let's say we have a function is equal to x cubed e raised to the 4xy squared. And let's evaluate the partial derivative with respect to x and y at the point 2 comes 0. So how can we find fx and fy? Now here's what you need to be careful. When we look for f of x, you need to use the particle, because the x variable is in the first part of the function and is in the second part. But when we find fy, you don't need to use the particle. So for example, let's say if you have 4x to the fifth, you have a constant multiplied by a variable. You do not need to use the particle here. This is simply going to be just 20x to the fourth. Now let's say you have 4x squared times e to the third. Here you have a variable and a constant. You don't need to use the particle. This is simply going to be ax e to the third. However, if you have 4x squared times e to the 3x, you have a variable and a variable here, so you do need to use the particle. So in the case of this problem, when differentiating with respect to x, we have an x variable here and here, so we use the particle. But when differentiating with respect to y, x is treated as constant, so we have a y variable on the right, but we don't have a y variable on the left. X is treated as constant, so we don't need to use the particle in that case. So I'm going to just help you see when you use the particle and when you shouldn't. So let's start with fy, because we don't need to use the particle. So it's going to be the constant, which is x cubed, and then all we have to do is differentiate e to the 4x y squared, which is going to be the same thing, e to the 4x y squared times the derivative of 4x y squared. So 4x is the constant, and the derivative of y squared is 2y. So now we plug in point 2 times 0. So x is 2, it's going to be 2 to the third, and we have e raised to the 4 times 2 times 0 squared. 0 times anything is 0. And it's going to be 4 times x, which is 2, times 2, and y is 0. So because we have a 0 here, the whole thing is 0. So that's the partial derivative with respect to y. Now let's find it with respect to x. So let's review the particle. Let's say we have two functions, f times g. You need to differentiate the first function, so you can get f prime times the original of the second plus the original of the first times the derivative of the second. So that's how we use the particle. So first let's differentiate the first part, x cubed, which is 3x squared, and then we're going to rewrite the second part, we're not going to change it. Plus, we're going to rewrite the first part, x cubed, and then differentiate the second part. So the derivative of e to the 4xy squared with respect to x is going to be e to the 4xy squared, and the derivative of 4xy squared with respect to x is going to be 4 times y squared, where y squared is a constant. So because the variable x was in both parts, we have to use the particle. Now let's plug in point 2 times 0. So x is 2, and because we have a y squared, 4xy squared becomes 0. So this will be e to 0 again, and we have a y squared here, so this whole thing will be 0. It's 2 times 1 part. So first let's differentiate the first part, x cubed, which is 3x squared, and then we're going to rewrite the second part, we're not going to change it. Plus, we're going to rewrite the first part, x cubed, and then differentiate the second part. So the derivative of e to the 4xy squared with respect to x is going to be e to the 4xy squared, and the derivative of 4xy squared with respect to x is going to be 4 times y squared, where y squared is constant. So because the variable x was in both parts, we have to use the particle. Now let's plug in point 2 times 0. So x is 2, and because we have a y squared, 4xy squared becomes 0. So this will be e to 0 again, and we have a y squared here, so this whole thing will be 0. 2 squared is 4, and 3 times 4 is 12. Anything raised to 0 powers 1. 2 to the third is 8, and 4 times 0 is 0. So this is going to be 12, and 8 times 0 is 0, so the final answer is 12. So the first derivative with respect to x is 12, and the first derivative with respect to y is 0. Consider this problem. Let's say f of x comma y is equal to 3y to the fifth divided by x cubed plus y cubed. So go ahead and find the partial derivative, the first one with respect to x and with respect to y. Now here's a question for you. Do we need to use the quotient rule? If you recall, let's say if we wish to differentiate f divided by g, where f and g are both functions that contain variables, it's going to be g f prime minus f g prime over g squared. Now, when differentiating with respect to x, 3y to the fifth is a constant, and x cubed is a variable, so we don't have a variable on the top and on the bottom. So for f of x, we don't need to use the quotient rule. Now, when differentiating with respect to y, we have a y variable on the top and on the bottom, so we do need to use the quotient rule with respect to y. And so that's how you can tell. So let's start with f of x, where we don't need to use the quotient rule. So imagine if you were differentiating, let's say, 4 over x cubed plus 7. If that's the case, what you could do is rewrite the function as 4, x cubed plus 7 to minus 1, and simply use the particle. And that's what we're going to do in this example. So first I'm going to rewrite it as 3y to the fifth times x cubed plus y cubed raised to minus 1. So f of x is going to be the constant 3y to the fifth. Then I'm going to take the negative 1, move to the front. So it's going to be times negative 1, and then we keep the stuff that's inside the brackets the same. Subtract negative 1 by 1, and that's going to be negative 2, and then differentiate the stuff on the inside. The derivative of x cubed squared, and derivative of y cubed is 0 because we're going to treat it as a constant. So this is going to go to the bottom, making this x point positive. And everything else will stay on top. So we have 3 times 3, which is 9, plus negative sign. So it's negative 9 x squared y to the fifth divided by x cubed plus y cubed squared. So that's the first derivative with respect to x. Now let's find fy, the first derivative with respect to y. And we have to use the quotient rule. So f is going to be the top function, 3y to the fifth. G is the bottom part, x cubed plus y cubed. Now f prime with respect to y is going to be 3 times 5y to the fourth, which is 15y to the fourth. G prime with respect to y is going to be 3y squared. the derivative of x cubed, which we're going to treat as a constant, is 0. So now let's plug it in into this formula here. So f of y is going to be g, which we know g is just x cubed y cubed, times f prime, which is 15 y to the fourth, minus f, which is 3 y to the fifth, times g prime, which is 3y squared, all divided by g squared, which is x cubed plus y cubed squared. So now let's see what we can do to simplify this expression. So if we want to, we can distribute 15 y to the fourth, or we can factor out 3 y to the fourth. Let's factor out 3 y to the fourth. If we do so, we'll be left with a 5 times x cubed plus y cubed, so that's 5x cubed plus 5y cubed. Now here we still have the 3 and y to the fourth, so we're left over with y. And that y is going to be multiplied by 3y squared, so it's negative 3y cubed. Don't forget about the negative sign. Divided by this f. So we can combine 5y cubed and 3y cubed. So the final answer is 3y to the fourth times 5x cubed plus 2y cubed divided by x cubed plus y cubed squared. So that is f of y.
Like a phrase. So I can type in whatever string of text I want here, and this will get stored inside of this variable, which, like I said, is technically called an array. Now, it's important to note that doing something like this, or creating this like string of characters, is a little bit different from these guys up here. So like these variables up here, we could modify them, we could give them new values, but you can't do stuff like that with this. So just know that this is like a special type of data, and it's going to act a little bit differently than these ones up here. But that's sort of the basics of working with data, and those are all the basic data types that we're going to be using in our C programs. In this tutorial, I want to talk to you guys some more about the printf function. So if you've been following along with this tutorial, we've been using an instruction in our C programs called printf. And printf basically allows us to print different things out onto the screen. In this tutorial, we're going to talk more about what printf does. We're going to look at how we can use it to print out things like variables, and also things like different data like numbers and strings and all that stuff. So in order to use printf, we just type out printf, and we're going to make an open and close parentheses and a semicolon. Now printf is what's called a function. And basically what that means is it performs a specific task or a specific function. In our case, printf just prints something out onto the screen, right? The task that it's doing is printing something out. And it basically works how you expect it to work. So if I came in here, I could print out a specific piece of information. And generally when we're using printf, we're going to be printing out text. So I can make an open and close quotation marks, and I can print out like hello world in here. Now this will print out onto the screen, hello. And inside of printf, I can use all sorts of special characters. So if I want to create a new line, for example, I can make a \n, and down here I can type world. And now this will print out a new line. So you'll see hello world on different lines. We can also use these special characters. So for example, I can print out like a quotation mark. So if I just print a normal quotation mark right here, you'll notice that it's messing this up. So it's sort of like counting this as the entire string. If I want to change that, I can just put a \, here, and now this will literally render a quotation mark. So I run my program and see we have a quotation mark there. So that's kind of like the basic usage, right? You can specify some text that you want to print out onto the screen, and it'll do it. But this printf function is actually extremely powerful, and we can use it to print out different pieces of information. So in addition to just printing out plain text inside of these quotation marks, I can also print out other types of information. For example, I could print out a number. And if I wanted to print out a number, I would have to use something called a format specifier. A format specifier basically tells this printf function that we want to print out a type of data that's not just plain text like this. So if I said %, and I said D, this would actually allow me to print out a number. So generally when we use these format specifiers, we use this %, and that tells C that you're going to want to print out something special. And then after that, we would type in a specific letter, and that'll tell C what exactly we want to print out. So if I said %D, this means that we want to print out an integer. So all I have to do now is I can make a comma, and over here, I can specify the integer that I want to print out. So I can say like 500. And now this is going to print out 500 to the screen. So you can see over here we're getting 500. And this is cool because we can interweave these different types of data with text. So I can say like my favorite number is %D, and this acts as a placeholder for this number over here. So when I run my program, now it says my favorite number is 500, and that's really cool. We can also use multiple format specifiers. So in addition to just using this %D, I can also specify another one. So over here I can say %S, and you'll notice that this is structured similarly to %D. %S is basically going to allow us to include some text. So I can include some more text just like this. So if I say %S, I can make another comma here, and I can say number. And now this is going to print out my favorite %S. So it's going to look for this string of text over here. It's going to insert that in, and it's going to say 500. So now when we run this, it'll say my favorite number is 500. And you'll notice here that I'm using multiple commas. So I'm saying like %S, %D, and over here I have a comma, and I'm specifying the string that I want to print, so the string of characters, and then the integer. And so basically the order that you put these format specifiers inside of your string of text is the order that you need to include them using these commas. So you're going to separate each of them using a comma. So in addition to %S and %D, we can also use a bunch of other ones. And I'm going to talk to you guys about some of the most common. %D will print out an integer like 500, but if we want to print out a decimal number, for example, a double, we say %F, and this is going to allow us to print out a decimal number. So I can say like 500.98754. And now this is going to print this out onto the screen. Actually, I need to build this. So my favorite number is 500.97540. So essentially you can use these printfs and you can use these format specifiers in order to include different data types into your output. So like this is just some general text output, and we can use these different guys to interweave like numbers or other strings and stuff like that. And where these really become useful is when we have variables. So if I was to create like a number variable up here, we call it like fav num, set equal to 90. I can use this variable and print it out inside of this printf. So over here we can make this %D, and instead of printing out
Mein Bruder.
Mein Bruder.
Meine Schwester. Und mein Mann. Eine Mutter.
Eine Mutter. Was?
Eine Mutter. Ein Vater.
Eine Mutter, ein Vater.
Mein Mann und meine Mutter.
mein Bruder, meine Schwester.
Eine Mutter und ein Vater.
Meine Schwester und mein Bruder.
Meine Schwester und mein Bruder.
Bonjour, Marie.
Bonjour, Marie.
Salut Paul, comment ça va? Salut Paul, comment ça va? Oui,
Oui.
Très bien. Et toi?
Je suis. Bonjour, Paul. Et toi?
Bonjour, comment ça va? Ça va bien.
Je suis Paul. Et toi?
Oui. Merci.
ça va très bien.
Bonsoir.
Bonsoir. Marie.
Perdón, Luis.
Perdón, Luis.
Buenos días, mucho gusto.
Buenos días, mucho gusto. Buenos días, good morning. Nice to meet you.
No.
Adiós, Juan.
Buen días. Mucho gusto.
No, lo siento.
Oh, sorry.
Gracias. Adiós.
Hola. Mucho gusto.
Hola, yo soy Juan.
Lo siento, perdón.
Perdón. De nada, Juan.
Don't worry about that one.
Agua.
Leche.
N. N. Ни. Са. Са. Я. Я. На. Ма. На. Си. Я. Б. 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 Ня. Ня. Би. Бан. Бан. Сам. Сон. Он. Был. Был. Б. Я. С. Н. С. Нос.
¿Tú hablas español?
Tú hablas español. Tú hablas, que tú.
Yo hablo inglés.
Yo hablo inglés.
Tú hablo español.
Tú hablo. Yo hablas. No. Tú hablas.
Habla español.
Yes.
Disculpe.
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 Yo hablo inglés.
Inglés.
Sí, hablo es. Yo hablo.
Hablo.
Disculpe.
Sí, yo hablo español. Yo hablo.
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 Hola, ¿hablas inglés?
¿Tú hablas inglés?
Au revoir, bonne soirée.
Au revoir, bonne soirée.
Merci beaucoup, Paul.
Merci beaucoup, Paul.
Bonne nuit.
Bienvenue. Bonne nuit, Paul.
Nuit.
Bon, bienvenue.
Au revoir. Bonne journée.
Au revoir, à bientôt.
Bonjour, Paul. Enchanté.
Bonjour, Marie. Enchanté.
Mein Vater ist groß und nett.
Mein Vater ist groß und nett.
Meine Frau, meine Tochter.
Meine Frau, meine Tochter.
Ich bin sehr klug.
Meine Frau ist sehr klug.
Meine Mutter ist nett und groß.
Mein Bruder ist sehr nett.
Meine Mutter, meine Tochter.
Ich bin sehr nett.
Mein Vater ist groß.
Scusa, tu sei Anna, vero?
Scusa, tu sei Anna, vero? Tu sei Anna, vero?
Ciao, di dove sei?
Ciao, di dove sei? Where you from, bro?
Salve. Tu sei Laura, vero?
Sono.
Fantastico. Io sono di Roma.
Tu.
Ah. Io sono di Milano.
Sei Luca.
Di dove sei?
Scusa, tu sei di Filadelfia, vero?
Scusa, tu sei di Roma, vero?
Io sono di Filadelfia.
Oh no. Okay.
旅人さん、どうぞ前へ。
どうぞどうぞ。ちょっと待った。ちょっと。ひょっとして今そこにいらしたのは旅人さんたちかい？
そうですよ。案内は私。
どうでしょう、お集まりの皆さん。まだ始まって間もないことですし、もう一度頭からやり直すというのは
いや、それは文句なし。
明暗だ。
最初からやって。
ありがとうございます。
よーし、決まりですね。はるか昔、遠くの国で迫害され追われた人たちがいました。
どの国も我々を受け入れてくれない。
食べ物はとっくの昔に尽きた。
このままでは子供たちが死んでしまう。
彼らは長い長い放浪の旅を続け、ある日深い森の中に迷い込んでしまいました。
お母さん怖いよ。もう歩けないよ。
もう少しの辛抱よ。でもこの子たちにあげられるものは何もないわ。見て、木の実が落ちているわ。
本当だ。よく見れば獣たちもいる。しかし恐ろしいように見えたこの森の恵みは豊かで、飢えていた人々の命を救ってくれたのです。
なんて美しい森なのでしょう。
ここには俺たちを嫌う者はいない。
石を投げて追い払われることもない。
うん。
ここでくださいよ。
そうだ。ここに国を作るのだ。
この森を永住の地に決めた彼らは豊かで美しい国を作りました。それから数えきれないほどの時が流れ、そしてね、私が今ここにいるの。その流れの先頭にいるの。キノさん、料理上手なんですね。
大した手際だ。
美味しそうね。
キノ、焼くだけだからね。味付け禁止だよ。
分かってるよ。
これを使って旅人さんの服が汚れたら大変だから。
ありがとうございます。
とってもお似合いです、キノさん。
なんか楽しそうじゃん。
エルメス、起きた？朝ごはんを食べたら買い出し、それとカノンを受け取りに行くよ。驚きました。初めてこれを手にした時以上です。
そうかい。
お代はいかほどですか？
いらん。ちょっと聞きたいんだが。
はい。
昔自分の教え子には師匠と呼ばせている凄腕のパースエイダー使いがいた。旅人であちこちの国でトラブルに首を突っ込んでは睨まれたり感謝されたりした。だいぶ前の話だ。その人のこと知らないかな？
いいえ、知りません。
わかった。それとな。誕生当時は森の人と呼ばれた。こいつを旅人さんに使ってほしい。こいつは昔私が旅をしていた時何度も身を守ってくれた。でももう何十年も使っていない。私は年を取ったし旅にも出ない。こいつはまだまだ使える。私と一緒に朽ち果てさせるのは惜しい。昔みたいにこいつに旅をさせてやりたいんだ。受け取ってくれるね？
わかりました。使わせてもらいます。
よっしゃ、そうこなくっちゃな。ついてこい。まずは試し撃ちだ。癖を教えてやる。ホルスターもグリップもいじってやらないとな。さあ。
キノさん。
こっちは暇で暇でしょうがなかったよ。
悪かったよ、お待たせして。じゃあ帰ろうか。
ちょっと待ってください。キノさんにエルメスさん。その前にもう一つ、ぜひお連れしたいところがあるんです。
すごいね。
綺麗。
ここが私の一番好きな、一番素敵だと思う場所です。いつか お客さんが来たら絶対に案内しようと思っていて、キノさんたちが最初です。
光栄だな。
私、将来はお父さんやお母さんの後を継いで立派なホテルの支配人と観光案内人になりたいんです。なれるかな？
なれるさ。いや、もうすでに立派な案内人だよ。この2日間僕はとっても楽しかった。
上に同じ。こんな素敵な国にはこんな素敵なガイドさんが似合うね。
ありがとう。私、もっともっといろいろなことを知って、もっともっと素敵な案内人になりたいんです。私の生まれたこの国にもっともっと大勢の旅人さんが訪れて、その人が一生忘れられないような素敵な思い出をたくさんたくさん作って帰っていくんです。そのお手伝いができるなんて素敵でしょ？
はあ、とっても素晴らしい仕事だ。
ねえ、キノさん、旅をしていて嫌なこととか辛いことはあります？
あるよ、たまにね。
旅をやめたい？
いや、それでも続けるだろうね。
それはキノさんがするべきことだと思っているからですか？
僕がやりたいことだと思ってるからさ。
ねえ、さくら。さくらさえよければ旅に出てもいいのよ。キノさんみたいにあちこちを回って、それから案内人になってもいいじゃない。
そうかな。私はどこも行かないよ。ここで勉強して、ここで一番の案内人になる。それが私の夢だもん。
そう、それもいいわね。
じゃああと少ししたら私たちは暇になるのかな。
その通り。
Zelda, no.
キノさん、ここです。
ずいぶん早く結婚するんだね。
普通は20歳を過ぎてから結婚するんです。珍しいです。
何をしているの？
新郎新婦が小さな袋をたくさん投げるんです。その中に欲しい子供の数だけ木の種を入れた袋が混ぜられています。その種を持って明日の朝を迎えた人が次に幸せな花嫁になれるって言い伝えがあるんです。
僕も探してあげようか。一人より二人だ。いい
ですか？
いいよ、行こう。
私たちは
5人子供が欲しいと思っています。
はい、これ。昔から運だけはいいんだ。
私、今まで拾えたことないんです。いつか欲しいと思ってたんです。ありがとうございます、キノさん。
どういたしまして。
キノさん、エルメスさん、そろそろ出国の準備をお願いします。
No, I'm gonna skip. It's way too painful.
ねえ、キノ。
ん？
これからどうするの？
そうだな。
なんとなく
歌おうかな。
Oh, oh man, oh no, I've read this too.
ひどいな。こんなひどいことをするのは一体誰？
私がキノと名乗る旅人と出会ったのは、まだ私が生まれた国に住んでいた頃。私が11歳の時だ。その時私は何て呼ばれていたのか、実はもう覚えていない。何か花の名前で読み方を少し変えると、とても嫌な悪口になっていたことだけ ぼんやり覚えている。よくそれでからかわれたから。も
やあ。お嬢ちゃん、こんにちは。
こんにちは。
僕はキノって名前だ。あちこち旅しているんだ。この町にホテルはないかな。ちょっと安くてシャワーがあるのがいいな。もし知っていたら教えてほしいんだ。
うちがそうだよ。お父さんお母さん、お客さん。
ようこそ旅の方。
ようこそ。
さあ、お部屋に案内します。
お願いします。ありがとう。やあ、おはよ
何をしているの？
う。モトラドを直しているんだよ。僕にこれを売ってくださいって頼んだら、そんなものは昔のゴミだからいらないって言われてね。もらったんだ。
治るの？
直すのさ。
I remember reading this. It uses a different kanji. It feels better.
やあ。
近くで見てもいい？
どうぞ。これは僕が昔一緒に旅をしていたやつにそっくりなんだ。あと1日もするとこいつも元気に動き回れるようになるだろう。
モトラドが動き回るの？
正確にはね、こいつは一人では動けないんだ。誰かが乗って契約しなきゃいけない。
契約って何？
この場合はお互いに助け合う約束をすることさ。
どうやって助けるの？
それはね、僕一人ではモトラドみたいに速く走れ。
Now let's say you're given a function that looks like this: x squared y cubed, and you want to find the slope of the surface in the x and y direction at the point 3, 2. All you need to do is find fx and fy and evaluate the function at this point, and that's going to be the slope of the surface in the x and y direction. So to find the slope in the x direction is simply fx 3, 2. So we just plug in. Well, first we have to find fx. Fx is going to be the derivative of x squared, which is 2x, times the constant y cubed. So fx 3, 2 is going to be 2 times 3 times 2 to the third power. 2 times 3 is 6, 2 to the third power is 8, and 6 times 8 is 48. Now let's find fy. That's going to be x squared times 3y squared. And so fy, the slope of the surface in the y direction, is going to be, this is fy 3, 2. It's going to be 3 squared times 3 times 2 squared. 3 squared is 9, and 2 squared is 4. 3 times 9 is 27, and 27 times 4 is 108. So these are the answers I'm looking for. Now sometimes you may have a function with 3 variables instead of 2. Let's say we have f of x, y, and z, and is equal to x to the fifth, y squared, z to the fourth. Now let's find the first 3 partial derivatives with respect to x, y, and z. So what's the partial derivative with respect to x? Now the rules are the same. We're going to treat x as a variable, and every other variable we're going to treat as a constant. So the derivative of x to the fifth is 5x to the fourth. So y squared and z to the fourth will be treated as a constant, and according to the constant multiple rule, we just multiply the derivative of the variable times the constant to get the derivative of the function with respect to that variable. So that's f of x. Now let's find f of y. So x to the fifth is a constant. All we need to do is differentiate y squared, which is 2y, and z to the fourth is the same. So when we look for f of x, differentiate just x to the fifth. When we look for f of y, differentiate only the y squared part. And when we look for f of z, differentiate just the z to the fourth part. So f of z is going to be x to the fifth, y squared, times the derivative of z to the fourth, which is 4z cubed. And so that's how you find partial derivative with respect to x, y, and z. So let's say w is equal to z to the third times ln zy times e raised to the x squared y cubed z to the fourth. So find dw dz, dw dy, and dw dx. Feel free to pause the video and be careful with this one. So let's start with dw dx. So do we need to use a product rule for this? In terms of x, we have a constant and a constant and a variable. So we do not need to use a product rule. So z to the third is a constant, so we can write ln zy will be treated as a constant. And the derivative of e to u is e to u times u prime. So it's going to be the same thing, e x squared y cubed z to the fourth times u prime, or the derivative of x squared y cubed z to the fourth. X squared is the only variable, so we should differentiate that part, which is 2x, times the constant y cubed z to the fourth. So that's dw dx. Now, what about dw dy? Do we need to use a product rule? It turns out we do. Here we have a constant, here is a variable because there's a y in it, and here this is another variable. So we got 2 variables multiplied to each other. So therefore, we need to use this form of the product rule. The derivative of two variables multiplied to each other is the derivative of the first times the second, plus the first times the derivative of the second. So the first part is this part, because that's the first time the variable shows up, and this is the second part, and that's just a constant. So we can write a constant, z to the third. And then let's differentiate the first part, ln zy. The derivative of ln u is u prime over u. So the derivative of zy is simply z times 1 over z, which is differentiating the y variable, divided by the original zy, times the other function, which is e x squared, y cubed, z to the fourth. So this part is like f prime, and this is g. Now for the second part. So let's rewrite the constant z to the third. F is basically the first time z variable ln zy, which we're going to rewrite as ln zy. And then g prime, the derivative of the second part. That's going to be e to u, which is e x squared, y cubed, z to the fourth. And then times u prime, which will differentiate y variable. So it's going to be x squared times the derivative of y cubed, which is 3y squared, times the constant z to the fourth. Remember that space. So we can get rid of this one. And let's simplify what we have. So we can cancel z. And we can combine z to the third and z to the fourth. So dw is equal to z to the third times e x squared y cubed z to the fourth divided by y plus 3x squared y squared z to the third times z to the fourth, that's z to the seventh. And then ln zy times e x squared y cubed z to the fourth. If you want to, you can factor out e x squared y cubed z to the fourth, and you can also take out z to the third if you want to. We're not going to worry about that, so I'm just going to leave the answer the way it is. Now let's find the other one, dw dz. So notice that z is found in each term, so we need to use a product rule with three variables. That's f times g times h. So it's going to be the derivative of the first part, f prime, times the other two, plus f times the derivative of the second part, times h, plus fg times the derivative of the third part, h prime. So in this particular example,
Okay, that makes it's very good. Okay.
z to the third is basically f, ln zy is g, and h is the e raised to all of that stuff. So let's find f prime. That's going to be 3z squared times everything else, ln zy, and e to the x squared, y cubed, z to the fourth, plus f, which is z to the third, times g prime. So that's going to be u prime of u. The derivative of zy with respect to z is simply y, divided by the stuff on the inside, which is zy, and then times e to the x squared, y cubed, z to the fourth. And then plus the third part, which is going to be z to the third, times ln zy, times the derivative of this thing, which is e x squared, y cubed, z to the fourth, times the derivative of the exponent, which is x squared y cubed, times 4 z to the third. So that's the answer for dw dz. You have to use a product rule with three different variables. When you do three variables, I mean f, g, and h. But z is just one variable, that's the only thing that would differentiate. Now let's see if we can simplify our expression. Let's factor out the base times factor. So we can take out e to the x squared y cubed z to the fourth, that's a common term. And we can also cancel a y, and z will cancel, so that becomes a z squared. So we can take out a z squared from every term. So let's put that here. Now, so this is gone, and we take out the z squared. So we're left over with 3 times ln zy. In the second term, we took out this, all of that is gone, and we took out all of the z squared. So there's nothing left in the second term, so we just put a 1. For the last term, we took this out. We took out z squared, so we're left with z, and we have ln zy and everything here. So it's going to be 4 x squared y cubed, and then z to the third times z. That's going to be z to the fourth, and then ln zy. So we can write the final answer like that if we want to. But that's the only thing that would differentiate. Now let's see if we can simplify our expression. Let's factor out the base times factor. So we can take out e to the x squared y cubed z to the fourth. That's a common term. And we can also cancel a y, and z will cancel, so that becomes a z squared. So we can take out a z squared from every term. So let's put that here. Now, so this is gone, and we took out the z squared. So we're left over with 3 times ln zy. In the second term, we took out this, all of that is gone, and we took out all the z squared. So there's nothing left in the second term, so we just put a 1. For the last term, we took this out. We took out z squared, so we're left with z, and we have ln zy and everything here. So it's going to be 4 x squared y cubed, and then z to the third times z. That's going to be z to the fourth, and then ln zy. So we can write the final answer like that if we want to. Now let's say if we have this function. And all we want to do is evaluate the first partial derivative with respect to y at the point 1, 2, 3. So x is 1, y is 2, z is 3. Go ahead and try that. So first, let's find fy. So the derivative of y squared is 2y. The second term doesn't have a y variable, so the whole thing's constant, that becomes 0. And the derivative of y is 1. So that's fy. So now we can evaluate at the point 1, 2, 3. So x is 1, and y is 2. And z is 3. So 2 times 2 is 4, and 3 to the fourth power is 81. That's 3 times 3 times 3 times 3. 4 times 4 is 16. Now 5 times 8 is 40, so 5 times 8 is 400. And 5 times 1 is 5, so 5 times 81 is 405. Plus 16, that's 421. So that's the rate of change of the function with respect to y at the point 1, 2, 3. So sometimes you may be asked for y. The second term doesn't have a y variable, so the whole thing's constant, that becomes 0. And the derivative of y is 1. So that's fy. So now we can evaluate at the point 1, 2, 3. So x is 1, and y is 2. And z is 3. So 2 times 2 is 4, and 3 to the fourth power is 81. That's 3 times 3 times 3 times 3. 4 times 4 is 16. Now 5 times 8 is 40, so 5 times 8 is 400. And 5 times 1 is 5, so 5 times 81. Is 405 plus 16, that's 421. So that's the rate of change of the function with respect to y at the point 1, 2, 3. So sometimes you may be asked to identify just one of the partial derivatives at a certain point. And that's how you do it. Now sometimes you may need to find higher order partial derivatives. So let's talk about the difference between the first derivative and the second, and the different forms in which they can come in. So let's say we have our original function f. If we differentiate f with respect to x, we can get the first derivative with respect to x, which is known as f of x. We can also differentiate f with respect to y, and we'll get the first partial derivative with respect to y, which is known as fy. Now at this point, we can differentiate the first derivative with respect to x. So the second derivative is going to be f xx, which means that we found the derivative with respect to x twice. Now we can differentiate fx with respect to y, and we'll get f xy, which means that we differentiate first with respect to x, and then second we differentiate with respect to y. Now fy, we differentiate with respect to x, and we'll get fyx, which means that we differentiate first with respect to y, and then with respect to x. Or we differentiate fy with respect to y, which is fyy, which means we differentiate the function twice with respect to y. So when dealing with second partial derivatives, if you have a function with two variables, there are 4 derivatives that you can get. Now let's say if we have the function x to the third plus 4x to the fifth y cubed plus 5y to the fourth. So find all 4 second partial derivatives. So find fxx, fxy, fyx, and fyy. Feel free to pause the video. So first, let's find fx. Let's find the first partial derivative with respect to x. The derivative of x cubed is 3x squared, and the derivative of x to the fifth is 5x to the fourth times the constant y cubed, and 5y to the fourth is a constant, so that's going to be 0. So that's fx, which we can write as 3x squared plus 20x to the fourth y cubed. So now let's find f double x. So 3x squared will become 6x, and x to the fourth is 4x cubed. And 20 times 4 is 80, so we can write it as 80x cubed y cubed. So that's our first answer. Now let's find f x y. So let's differentiate this function with respect to y. 3x squared becomes 0, and the derivative of y to the third is 3y squared. So this is 60 x to the fourth y squared. And so that's it for this one. Now let's find fy. So we find fyx and fyy. So x cubed is now a constant, that becomes 0, and y cubed, the derivative of that is 3y squared, and the derivative of y to the fourth is 4y cubed. So fy is equal to 12 x to the fifth y squared plus 20 y cubed. Now from this function, we find the other two answers we're looking for. So let's find f of y. Let's differentiate with respect to y one more time. So it's going to be 12 x to the fifth times 2y plus 20 times 3y squared. So that's equal to 24 x to the fifth y plus 60 y squared. So that's f of y. Now let's find fyx. So let's differentiate this function with respect to x. The derivative of x to the fifth is 5x to the fourth. And with respect to x, y cubed is constant, so 20y cubed becomes 0. So the final answer is 12 times 5, which is 60, x to the fourth y squared. So that is the second derivative, where we differentiate with respect to y and then with respect to x. Isn't that a problem? Let's say f is equal to x cubed y to the fourth plus z squared x cubed y plus 4x cubed z to the fourth. So this time we're going to find a mixed partial derivative, but a third derivative instead of a second order derivative. So let's find the mixed third order derivative. Let's say f x y z. Go ahead and find. So first we gotta find f of x. We gotta differentiate the function with respect to x. So x cubed will become 3x squared, and then we have another x cubed, which is 3x squared again times y, and the derivative of 4x cubed is 12x squared z to the fourth. So now we're going to differentiate the function with respect to y. So y to the fourth will become 4y cubed, and the derivative of y is 1. Now 12x squared z to the fourth doesn't have a y variable, so that becomes 0. Now we're going to differentiate f(x, y) with respect to z. Now this term doesn't have z, so that's going to become 0. Z squared is 2z times 3x squared. So the final answer is 6zx squared, or 6x squared z. Now let's try another example, using the same function. This time, let's find f, y, x, x. So first let's find fy. So this becomes 0 because there's no y variable. The derivative of y to the fourth is 4y cubed, and the derivative of y is simply 1. So this is what we have left over. Now let's find fyx. Let's differentiate this function with respect to x. The derivative of x cubed is 3x squared. Now let's differentiate that function again with respect to x. 3 times 4 is 12, and the derivative of x squared is 2x. And the derivative of 3x squared is 6x. So the final answer is 24xy cubed plus 6x z squared. So that's the third order mixed partial derivative, where we differentiate y. First, and then x, and then by x again. This is a theorem that you need to know related to this section, and that is the equality of mixed partial derivatives. So if the function is continuous, then you need to know that f x y is equal to fyx. So if you differentiate with respect to y once and with respect to x once, the order doesn't matter. These two mixed partial derivatives are equivalent to each other. So let's say if you want to find a third order derivative, f of x y z is the same as f of y x z, which is the same as f of z x y. All of these three mixed partial derivatives are the same. We differentiate with respect to x once, with respect to y once, and with respect to z once. The order doesn't matter. So here's another example. F of y x y is equal to f of x y y, which is equal to f of y y x. These are all the same. We're differentiating with respect to x once, but with respect to y twice. So let's prove it. So let's say we have a function that's x squared y cubed plus 4x y squared. And let's prove that f of x y is equal to fyx. So let's find f of x first. F of x is 2x y cubed plus 4y squared. Now let's find f of x. So let's differentiate with respect to let's find f of x y now. The derivative of y cubed is 3y squared times 2x. That's 6x y squared. And the derivative of 4y squared is 8y. So now let's find f yx. So first we gotta find fy using this function. The derivative of y cubed is 3y squared, so we're gonna have 3x squared y squared. And the derivative of y squared is 2y times 4x. That's 8xy. Now let's differentiate this function with respect to x. The derivative of 3x squared is 6x times y squared. The derivative of 8x is simply 8. So notice that these two are the same. Fxy is equivalent to fyx. Now let's say that f is 4x squared y cubed z plus 6x y squared z squared. And let's show that f of x y y is equal to f of y x y, and let's show that's equal to f y y x. So first, let's find fx. Let's differentiate this function with respect to x. So the derivative of 4x squared is 8x times the constant y cubed z. The derivative of 6x is 6, and then times y squared z squared. Now we need to differentiate fx with respect to y. So it's going to be the derivative of y cubed, which is 3y squared times 8. So that's 24x y squared z. And the derivative of 6y squared is 12y times z squared. Now let's differentiate again with respect to y. So y squared becomes 2y times 24. So that's 28x y z. And the derivative of 12y is just 12. So let me write this somewhere. Let's just separate this. So f of x y y is equal to 48 x y z plus 12 z squared. Let's write that for reference. We'll compare later. So now let's find f y x y. So first let's find f y. The derivative of y cubed is 3y squared times 4. So that's 12x squared y squared z. And the derivative of y squared is 2y times 6, which is 12xy z squared. Now let's differentiate that function with respect to x. The derivative of x squared is 2x. So 12x squared is 24x times y squared z. And the derivative of 12x is just 12y z squared. Now let's differentiate that function, this one, with respect to y. So the derivative of y squared is 2y times 24, that's 48x y z plus the derivative of 12y is 12. So notice that these two are the same. Now let's find the last one, f y y x. So let's find f y first, which we know is 3y squared times 4, that's 12x squared z. And y squared is 2y times 6, that's 12x y z squared. Now let's find the derivative of this function with respect to y. And 2y squared here, which I'm right. So the derivative of y squared is 2y times 12, that's 24x squared y z. And the derivative of y is 1, so times everything else, which is 12x z squared. Now let's differentiate this function with respect to x. The derivative of x squared, or 24 squared, is 48x. And the derivative of 12x is just 12. So as you can see, we're getting the same thing. So the order doesn't matter. The reason why these are the same is because we're differentiating with respect to y twice, and we're only differentiating with respect to x once. But the order doesn't matter. So mixed partial derivatives are the same if you differentiate each variable the same number of times, regardless of the order. So that's it for this video. So hopefully you have a good idea of partial derivatives and how you define them. So thanks for watching.
You speedrun, man.
Got this number, we can just access that variable. So I can say fave none. And this will allow me to print out that variable using that printf function. So my favorite number is 90. So that's the basics of using printf. This is a very awesome tool that we can use. And printf is basically just used for us to find out information. So when we're running our programs, a lot of times we're going to want to be able to get some information about what's going on, about what they're doing. And printf can allow us to do that. So don't be afraid to use these different access modifiers, like I said, %f, %t, %f. Those are all sort of the common ones. And you can also use %c, and this will allow you to print out a single character. So I can come over here, create like a character variable. We'll call it my char, and just set it equal to like lowercase I. And I can print this out using %c. So now we can say my char. And you'll see that we print out I. So play around with printf. It's extremely useful, and it's really going to come in handy when we're writing more complex programs. In this tutorial, I want to talk to you guys about working with numbers in C. Now, a lot of times when we're writing programs in C, we're going to want to do different things with numbers, whether that's just storing numbers and keeping track of them, or adding, multiplying, subtracting, doing math with numbers, or really just dealing with numbers in general. So I'm just going to give you guys a basic overview of a lot of the stuff we can do with numbers. We're also going to talk about how different number types interact, so how like integers and doubles interact and all that fun stuff. So down here, I'm printing out a number. So you can see I'm using this printf function, and inside of these quotation marks, I'm basically saying %f. And %f stands for like a floating point number, so that could be either double or float, basically a decimal number. So when we put %f in here, it's going to allow us to print out a decimal number, just like this. And you can see I can run my program and it'll print out 8.9. You'll notice it's printing out not just 8.9, but it's also printing out to a very precise decimal point. And that's what C is always going to do. So it's always going to print it out to a very precise decimal. So using these decimals, I can do all sorts of stuff. So obviously I can just print out the decimal, but I can also do things like math. So I can say like 5.0 plus 4.5, and this is going to go ahead and be able to do that for us. So when I run my program, not only is it going to like print this out, but it's going to do the actual math operation. You see we get 9.5. So in addition to addition, we can also use subtraction, division, which is going to be a /, and multiplication, which is going to be an asterisk. And you can use all these different things to do the 4 basic math operations: addition, subtraction, multiplication, and division. So now we'll talk about how we can use floating point numbers, so like doubles and floats, alongside integers. So let's say I was going to add an integer with a double. So if I said 5 plus 4.5, well, actually when we do this, this entire answer is going to get converted into a decimal number. So when I say 5, which is an integer, plus 4.5, we're going to get a floating point number back. So we're going to get 9.5. And basically any operation that you do between an integer and a floating point number is going to return a floating point number back. So that's important to realize. But if I was to change this to 4, now this isn't going to work anymore because this is asking for a floating point number and we're giving it an integer. So when I do math with two integers, it's going to give us an integer back. And if I do math with a floating point number and integer, it'll give us a floating point number back. It's also important to realize, for example, if I took 5 and divided it by 4, this should actually be a decimal number, right? And you'd expect us to get a decimal back. But if I just printed out %d, so I printed out the result of the integer 5 divided by the integer 4, I'm actually going to get an integer back. So when I run the program, you'll see we're getting a 1 here. But really, this like the answer is 1 technically, but it's 1 with a bunch of decimal points after it, right? It's 1 plus a bunch of other stuff. But when we just do math with two integers, we're going to get an integer back. If I was to say 5 divided by 4.0 and I printed out a decimal, now we're going to get the entire answer back. So we're going to get 1.25. So that's just a little bit about dealing with integers and floating point numbers. We can also take these and put these into variables. So in addition to just having numbers down here, I can specify a variable like num set equal to 6, and we can go ahead and print num out down here as well. We need to make this a d. So now we'll be able to print out that variable with no problem. So it can be really useful sometimes to store these numbers inside of variables. I also want to talk to you guys about using more complex mathematical functions. Now in C, we have these things called functions, which are basically just little blocks of code that we can call, and when we call them, they're going to go off and do certain things for us. So they'll like modify a value or give us information about a value. And these functions can be really useful. I'm going to show you guys a couple functions that we can use with math. So I'm just going to come over here and I can actually start using these functions, and all you have to do is just type out the name of the function that you want to use. So by default, C is going to give us access to a bunch of math functions that we can use. So we really don't have to do anything. All we have to do is just type in their names. And I'm going to show you guys one. It's just POW. So I'm just typing in POW. Then I'm going to type in open and close parentheses. And inside these parentheses, I can actually give this two numbers. What this is going to do is it's going to take the first number that we give it, and it's going to take it to the second number. So if I said like 2 and 3, and you notice I'm separating them with a comma, this is basically going to give us 2 raised to the third power. So it'll give us 2 cubes. So when I run my program, and actually we need to print this out as a decimal number. So this is going to give us a decimal number back. So I need to print this out with f. When I run my program, we're going to get 8 back, just like that. So it's basically cubing 2. I can say like 4 raised to the third power, and now we should get back 64, which we do. So that can be pretty useful. There's a couple other ones I'll show you. Another one is SQRT. So this will allow you to take a number's square root. So if I said like 36 in here, now we're going to print out the square root of 36, which is going to be 6. And there's a couple other ones. So let's say that I had a decimal. I could say CEIL, which stands for ceiling. So if I had like 36.7, which we do, raised to the third power, is it's going to take the first number that we want. It's just POW. So I'm just typing in POW. By default, C is going to give us access to a bunch of math functions that we can use. So we really don't have to do anything. All we have to do is just type in their names. And I'm going to show you guys one. It's just POW. So I'm just typing in POW. Then I'm going to type in open and close parentheses. And inside these parentheses, I can actually give this two numbers. What this is going to do is it's going to take the first number that we give it, and it's going to take it to the second number. So if I said like 2 and 3, and you notice I'm separating them with a comma, this is basically going to give us 2 raised to the third power. So it'll give us 2 cubes. So when I run my program, and actually we need to print this out as a decimal number. So this is going to give us a decimal number back. So I need to print this out with f. When I run my program, we're going to get 8 back, just like that. So it's basically cubing 2. I can say like 4 raised to the third power, and now we should get back 64, which we do. So that can be pretty useful. There's a couple other ones I'll show you. Another one is SQRT. So this will allow you to take a number.
Squirt. Kubert. Okay, next is. 15 minutes more of this. I'm gonna start drawing.
切れない。
昨日は痩せてるもんね。
モトラドは速く走れるけれど、誰かがまたがってバランスを取らないと転んでしまう。
うん。
そして僕はモトラドにまたがればうまくバランスを取ることができる。僕はバランスを、モトラドは走りを。そうすれば旅がもっと楽で楽しくなる。
それで助け合いの契約なのね。
そうさ。だからこいつが気がついたらどうですかって聞かなくっちゃ。
モトラドと話せるの？
もちろん話せるさ。今のうちに一緒にこいつの名前を決めようかな。何がいい？
キノの昔のお友達はなんて言うの？
エルメスさ。
じゃあそれがいい。
そうかい。
エルメス。
じゃあそうしよ
う。我はキノ。
おいしいね。ありがとう。
キノは何をしている人なの？
何って？
大人なんでしょ？
まあ君よりはね。
大人は何か仕事をしなければならないでしょ？
ああ、そうだね。本当はね。
じゃあどんな仕事をしているの？
そうだな。強いて言うのなら旅をしているかな。
旅っていろいろなところに行くこと？
ああ、そうさ。
嫌なことはある？
たまにはね。でも 楽しいことの方が圧倒的に多いかな。
それじゃあ仕事じゃないよ。仕事って辛いものなんだよ。楽しくないんだよ。もしも楽しいことがあるのなら旅は仕事じゃないよ。
そうかな。
だから私は明日あさって手術を受けるんだよ。
何の手術？
大人になるためのだよ。
それは一体何のことだい？もしよかったら教えてくれないか？
お前たち子供は好き勝手に行動していればいい。しかし大人には自分勝手な行動は一切許されない。なぜなら仕事をするからだ。でも安心しろ。お前たちが12歳になったら手術をしてやる。頭を開けてその中の子供を取り出すんだ。するとお前たちは一晩で大人になれる。全員嫌なことでも何でもきちんとできる立派な大人になれるんだ。
12歳の誕生日の前の1週間は最後の1週間と呼ばれているの。その間は大人からは子供に話しかけないし好き勝手に過ごしていいの。それと毎日特別なお菓子を1個ずつ食べられるの。
なるほどね。でも随分と乱暴な話だな。
なんで乱暴なの？手術のおかげでどんな子供でもちゃんとした大人になれるんだよ。
僕にはちゃんとした大人って一体何なのかわからない。嫌なことができるのがちゃんとした大人なのかな。嫌なことを延々に続けてそれで人生楽しいんだろうか。僕にはよくわからないね。
さっきキノは私より大人って言ったよね。じゃあキノは大人なの？
いや、君の言うところの大人では多分全然ないね。
じゃあ子供？
いや、君の言うところの子供でもないと思う。
じゃあキノは一体何なの？
僕かい？僕はキノさ。キノって名前の男。それだけかな。そして旅をしている。
好きなことを？
そうさ。僕は旅が好きだ。だから旅をしている。もちろんそれだけじゃ生きていけないから途中で見つけた薬草とかを売ったりしているよ。でも基本的には旅を、好きなことを、やりたいことをしている。
好きなことをしているの？
君の一番好きなことは何だい？
歌を歌うこと。
僕も歌うのは好きだ。旅の途中よく歌うんだ。さあ行こうどこまでも鳥のようにどこまでも川を渡って丘の向こうへそこに何かが待っている。下手だろ？
とっても。
ちっとも上手くならないんだけれど歌っている間は楽しいんだ。
森の花をあなたが幸せでありますように、あなたが笑顔でありますように。
上手だね。驚いたよ。今まで聞いた中で一番の歌い手さんだ。
ありがとう。
歌が好きなら歌手になるのはどうだい？
私は歌手にはなれないよ。
どうして？
だって私のお父さんとお母さん歌手じゃないもん。仕事を継がせるために大人は子供を産むんでしょ。昔からの決まりだよ。
そうか。お国の事情ってやつだな。
Okay, I'm gonna watch Butch is a Rock because oh man, what the hell is this? Oh, okay, I think I cringed too much. Didn't finish watching it. Okay. Oh yeah, I read the manga with. That's I mean, this is that's Tensura Tensura very good. But I need something else to watch, you know. Hunter x Hunter is okay. It's very good. Tougen Anki. Not interested. 追放者食堂。の消防隊。Chainsaw Man. I've already watched that. 香る花は凛と咲く。なんだ。追放された。Oh my god. Slop. Hey, fuck it. I'm gonna watch Slop. Slop will be watching.
歓迎するぜ。
Oh nah. We're watching Slop.
それではロイドが私たちのパーティーに。
Do they have it? They have it.
あったかいね。ほんまやね。秋にしてはいい買い物したわ。だろう。犬山さん、こんな感じかな。ええで。ほい、締まりにココア一丁。ありがとう。なでしこは？私は焚き火を堪能してからいただきます。斉藤さん、あんま火に近づけるとマシュマロ燃えるで。本当？意外と難しいねこれ。遠火でじっくりとが基本だよ。でもなかなか我慢ができひんわ。だよな。はあ。みんなで撮ろう。
I'm gonna get copyright strike again. Peace. Wanna go there. The thing is, I have to take the Shinkansen to Tokyo, then from Tokyo back to Fuji. I think I can take the Chuo line. It's more expensive. You know what? I'm gonna try like this autumn. I don't know when, but if I get the chance, if there's like a holiday that is quite long, I'm gonna go. I'm just gonna take the normal train, just to take in the scenery, you know. Yeah.
今日は雲でよく見えないか。もう2時だ。
Ooh, okay. Oh, November then. Okay, November.
What? なんだあれ。あれは確実に風邪ひくな。
Okay, so what's next? I want to draw, but the thing is I'm tired. Okay. I'm gonna wait for a while. I'm gonna mute the desktop audio. I'm just gonna basically just draw. Yes. How long have I been streaming? You know what?
Hold me close till I get up. Time is barely on our side. I don't wanna waste what's left. The storms we chase are leading us, and love is all we'll ever trust. Yeah, no, I don't wanna waste what's left. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. Finding life along the way, melodies we haven't played. No, I don't want no rest. Echoing around these walls, fighting to create a song. I don't wanna miss a beat. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. see the horizon, turn us to thousands, and we'll grow in number, fueled by them to see the horizon, turn us to thousands, and on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays, and on we'll go, through the wastelands, through the highways, and on we'll go.
I'm walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking, but there's no time for regrets. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. We are heroes tonight. We will fly above the sky. We are heroes tonight. Feel like a dynamite, ready to explode right up in the sky. I need you to listen, I need you to hear, and don't show any fear. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. We are heroes tonight. We will fly above the sky. We are heroes tonight. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul.
invincible.